Oh no, that is not good to hear. Was
No,
it like,
no, it's like if I just put like okay, so you see like the same question that you talked about the arc length.
yeah,
In the answer you had like in the workers you had pi over 6. I
yeah.
had pi over 6, but the answer was supposed to be pi over 3.
You sure it's only pi over 3?
Ha- Okay, now yeah, I'm confused because I know for the first part you had pi over 3, but I had pi over 6 because I didn't put it into half.
Wait, is it?
But
I'm
so
not
when
The
sure.
I
first
calculated,
part you
oh,
have to have
so,
pi
but
on
so
three.
when I calculated it back, I got back the same area. So I don't know if that was supposed to be the right thing or
Sus.
yeah, because when I saw pi over 6, I said I asked myself this question. I say, is this answer correct? Or if
Well,
it's not, I don't know. So I plug it back into the equation and I got back the same answer. So I just went with it.
mm,
Oh, it was pi over 6. Oh,
the
okay.
other one
Wait,
was pi
no.
on 6.
Oh, wait,
Yeah,
what? Serious? Wait, so
Yeah.
I calculated for the other thing then. Oh my gosh. So
Oh,
when I plug it in, right, I got back the same area, which was the 200 pi over 3, and I was like, okay.
I don't feel like we should I get pi over 3. You see this? You see like the area, the I mean the angle for the sector. The
Yes, sir.
angle for the sector was pi on 3, and the angle for farming was pi on 6. Yeah.
What? Okay.
Because
yeah.
because Nikolai, the whole thing is 90 degrees, right? 90 degrees is pi on 2.
Yes,
And so
sir.
if you want to find the green angle, you would take away the pi on 3 from pi on 2. It should be pi on 6. But I don't feel like we should talk about this. This is in the past. This is in the past. Now we need to focus on chemistry. I mean, not saying chemistry, but physics,
Eh,
physics, physics, physics,
okay.
physics. I tell you now, like, I'm not sleeping and it get into my head. Like, it gets into my head. Today I was with Mrs. Math Vibes and like, okay, once it's not maths, art, maths, or physics, I can't form a sentence, dog. I cannot form a sentence. I cannot form a sentence. It's crazy. It's concerning. It's concerning, to say the
No,
least.
but really and truly, sir, when I plug it back into the equation and I got back the area, I just
Yeah.
went with it. So I didn't even know that was for the second question.
We shouldn't talk about it. That is in the past. In the past.
So would I get a mark no or no?
I don't
Because
I don't
I
I don't
see
know,
that
Nikolai.
I see now that's supposed to be on the other side.
I don't know, Nikolai. But that's in the past. That's in the past. Let me focus on the present and let me focus on physics.
Paper
Right.
one's for you, sir.
Right, let me just put my phone on do not disturb. Alright, so the first one we're gonna look at is specific heat capacity. What is that? Does anybody know what specific heat capacity is?
Yeah.
Yeah.
So it's like, okay, the specific heat capacity, it is the
Heat
amount
energy.
of heat energy that is required, right, to change the
Right?
temperature
1 kilogram of
By
acetylene.
of 1
One,
kilogram, right? 1 kilogram
of a
by
substance
yeah,
by
one Kelvin.
of a substance by gosh, by 1 Kelvin.
1 Kelvin or degrees Celsius. That's the thing. That's the thing.
Oh, so
Or
you can't
degrees
mix it up.
Celsius.
You can't mix it up. You can't
Look,
put two of them.
you could put anyone. You could put anyone.
Oh, right.
I will explain all of that shortly, right?
Yes, sir.
But hear what, guys? Anytime you hear the word specific, just know the definition or whatever the calculation is. It will be with respect to mass and specifically 1 kg. So specific heat capacity is the amount of heat energy. Guys, did all of us, did we know that heat was a form of energy? We knew that, right?
Yes, sir.
Yes.
Sure.
If you didn't, now you know, right? So it's the amount of heat energy required, right? Required to change. the temperature of how much? What's the mass of the substance? Of
1
what?
kilogram. 1 kilogram.
Right. Right, so the amount of heat energy required to change the temperature of 1 kg of a substance by
By
what?
Kelvin.
1 Kelvin.
Or 1 degree
By
Celsius.
by 1 Kelvin or 1 degree Celsius. Now, this is a good opportunity to explain why delta T is not affected by Kelvin or degree Celsius. So, remind me, guys, how do you convert something to Kelvin?
Plus
Remind me.
273.
And 200.
Right.
Minus 273.
So it's theta plus 273. Cool. So here what? Let's say we had 25 degrees Celsius and we increase the temperature to 30 degrees Celsius. If I wanted to find delta T, that would just be 30 degrees Celsius minus 25 degrees Celsius. So what was the change in temperature there?
5 degrees Celsius.
It was just 5, right? We could just call it 5. We could just call it 5, right? Cool. If I converted 25 degrees Celsius to Kelvin, I'd have to add 273 to that. So what would 25 plus 273 be? Somebody tell me.
298.
298.
All right, so 25 degrees Celsius would be equivalent to 298 Kelvin. And what is 30 plus 273? That should be 303 Kelvin, right?
Yeah.
Yes, sir.
Yeah.
So here what I want you guys to do. I want you to calculate 303 minus 298 and tell me what you get.
5 Kelvin.
5. So I hope you guys could understand why delta T isn't affected by degrees Celsius or Kelvin. It will give you the same difference. You understand that?
Yes,
Yes,
sir.
sir.
Yeah, fair.
Are you all sure?
That is why I could include either one in the definition.
Yes, exactly. Now, when you're doing the gas laws, however, you have to use Kelvin because if you recall, kind of jumping into some things prematurely, but consider the graph of volume and temperature. If you use degrees Celsius, your graph is going to look like this. And if you actually want to get it to cut the x-axis, it actually cut the x-axis at minus 273 degrees Celsius. But I'm not sure if you know about that. That's actually how we come up with the Kelvin scale. Do any of you guys know that?
Yes, sir. My physics teacher did that. That was what she did
Okay.
in first.
Yeah,
Good,
I remember
because-
seeing this too when you was doing extrapolation and stuff.
Because minus 273 degrees Celsius is the temperature at which the volume is effectively what?
0.
0, correct. Because remember, when you freeze something, what happens to the volume?
It gets more dense.
Now remember what kinetic theory matter says. You have a bunch of particles and they are vibrating, right? They are vibrating. Now, when you add energy, they'll gain more energy and they'll start to vibrate more rapidly. And so they'll be able to break out from the bonds and the volume will expand. Now, conversely, if you're cooling something, are you adding energy or are you taking away energy? If you're cooling something,
No, you're taking it up. You're
Taking away energy.
taking away the energy. So if I'm taking away the energy from the particles, then are the particles vibrating or are they slowing down?
Slowing
Well,
down.
it will be slowing down because it releasing bonds, it breaking bonds.
Exactly. Well, I wouldn't say breaking bonds. So when you actually cooling a substance, the molecules and the particles actually they stop moving. And the point at which they stop moving is actually minus 273 degrees Celsius. Yeah. And it's theoretically impossible to reach minus 273 degrees Celsius. Because can you ever have zero for volume?
Nah.
No.
Nah.
No.
But it's just a theoretical point where the volume is 0 and the particle movement stops. Yeah, but anyways, this is what specific heat capacity is. It just tells us the amount of heat energy you'd have to add to a substance, to 1 kilogram of a substance, to raise the temperature by 1 Kelvin or 1 degree Celsius. Now, specific heat capacity is denoted by a capital C or common C.
Come on.
Common sense.
Come
Come
on,
on.
see, sir.
Good, common C. And let me show you something really cool, right? I know for a fact a lot of you guys watching this, you have trouble with the units. So to address that, I want somebody to tell me, what do we measure energy in?
Juice.
Joules.
We measure energy in joules. What do we measure temperature in?
Kelvin.
Kelvin. Or Celsius, degrees Celsius.
Right? Doesn't matter. In this instance, it doesn't matter. And it's 1 kg, right? So we're dealing with mass here. So what if I told you the units for specific heat capacity is joule per kg Kelvin? Would you be shocked? Or would that make sense?
Nah, that makes sense.
That makes sense.
That makes sense, right? Or alternatively, it could be joule per kg degrees Celsius. That also makes sense. And we know why it makes sense, because is the difference affected by the Kelvin or degree Celsius?
No, sir. No, sir.
No, it's not. It's not. So that is specific heat capacity. It's just simply the amount of heat energy you'd have to apply to a substance, 1 kilogram of a substance, to either increase or drop the temperature by 1 Kelvin or 1 degree Celsius. So do we have that on lock?
Yes, sir, for sure.
Yeah.
Yes, sir.
Yeah.
And again, specific heat capacity, it deals with change in temperature. I cannot stress that enough. This formula deals with change in temperature. Because isn't it the amount of energy you're going to apply to a kilogram of a substance to change the temperature?
Yes, sir.
Yes, sir.
Yes.
Does this deal with change in state?
No, sir.
No, sir.
No, this does not deal with change in state. This does not, I can't stress that enough. This does not deal with change in state. And the formula for this is E. If we want to figure out the energy, it's going to be the mass of the substance by the specific heat capacity by the change in temperature. You could write delta theta.
So I was now going and ask if when you're calculating specific heat capacity, if you just use MCAT.
Say that again?
I was just about to ask if when you're calculating specific heat capacity, if you just use MCAT method.
Oh, that's the same thing. That we're talking about the same thing. I think you're talking about like it's the exact same thing. You're talking about this?
Yes, sir.
Yeah, it's the same thing. So let me just address that one time. This and this, it's the exact same thing. You guys understand that, right? Or not?
Yeah. Because
Yes.
theta is just like the next way of saying temperature.
Exactly. This part over here is just change in temperature. That's all. And does it matter if the temperature is in degrees Celsius or Kelvin?
No, sir.
No, sir.
No, sir.
And I'm only going to use this formula when there is a change in.
Temperature, sir.
Temperature.
Temperature.
Cool. So here what? Speed round. Somebody tell me, what is the specific heat capacity?
The amount of energy required to change the temperature of 1 kilogram of a substance by 1 Kelvin or 1 degree Celsius, sir.
What's the formula associated with it?
So the formula associated with it would be the heat energy is equal to the mass multiplied by the specific heat capacity multiplied by the change in temperature, or you could say delta theta.
Cool. Earlier, when we start doing the questions and you see change in states, I don't want to hear anybody tell me MC delta theta. Eh? I don't want anybody to tell me MC delta theta. This is for change in temperature. Alright, the next one we're going to look at is heat capacity.
So I can go back up for my papaya, please.
Okay, take up a chair that fast. Alright, moving with speed, right? So take up a chair fast and I'll move on. Do you guys see the word specific here?
No,
No,
sir.
sir.
So will this definition have mass in it?
No, sir.
No, sir.
No. So what do you suppose heat capacity is?
The amount of heat energy required to raise the temperature of the entire object by 1 degree Celsius or Kelvin.
Exactly.
Yeah.
If it's heat capacity, we don't care about the mass. We don't care about the mass. right? The heat.
I kind of name too, so because if you listen to specific, the word specific means a particular mass, right?
Correct, correct.
Heat capacity is just the general term.
Correct. Change the temperature. So when we look at the units for heat capacity, are we gonna have kg in it?
No, sir.
No.
No. It's just going to be joules per Kelvin or
12 degrees Celsius.
cool. And we spoke about why the units you use for temperature in this instance does not matter because the change is going to be the same. So heat capacity is denoted by a capital C or a common C?
Capital, so
See,
Commons.
Capital C.
Oh,
And what is the formula linking heat capacity to specific heat capacity?
E is equal to MC.
yeah.
Well, I typically say C is equal to MC, but that's fine.
Yeah, I see.
Now let's see why this makes sense. Let's see why it makes sense from a unit standpoint. We know that the units for heat capacity is joule per Kelvin. We know that, right? Yes or no?
yes, sir.
Yes, sir.
yes.
Now
sure.
we know mass is kg, and we know that specific heat capacity would be joule all over what?
Kg delta theta.
Now kg Kelvin.
Kelvin, sorry.
If you recall, what the units for specific heat capacity is joule per kg Kelvin.
Yeah.
Now look at this, right? What would happen with the kgs?
The cancel.
Cancel.
And when you look at it, are you seeing what I seeing?
Yes, sir.
Yeah.
Right. Cool. So that is heat capacity. And the units are joule per Kelvin or joule per degree Celsius, and its capital C is equal to MC. Let us talk about the specific latent heat of fusion. LF. So again, you see the word specific here. So what will be involved in the definition?
Mass.
Mass. Can anybody tell me what specific latent heat of fusion is?
And that is when you're going from solid to liquid, sir.
Good.
But
When you
on
hear
the change in
or vice
temperature.
versa, right? Or vice versa. Or vice versa. Because the word fusion, when you think of fusion, don't you think of liquid to solid? Like fusing.
Yeah.
Fusing.
Sure.
Yeah. So this will be the amount of heat energy, right? Amount of heat energy required
Per kg.
right? Required to, right? I should use spread to convert 1 kilogram of a substance from what to what?
Solid to liquid or liquid to solid.
Like
Right. And this is important. This is very, very important. Without a,
change
Temperature.
in temperature.
Without a change in temperature, yeah.
this is the most important part. Without a change in temperature. Now, when you read this, you're probably scratching your head and saying, nah, I kind of confused. That don't make sense. How could you change the state without changing the temperature? And I promise you it makes perfect sense. Did any of you guys ever leave a bottle in the fridge? And like in the freezer, and when you take it out, you know, just like ice crystals out of form just by you picking it up?
Sure.
That happened to me so many
Yes, sir.
times.
Yeah, and the reason for that is because, please mute yourself. Okay, thank you. When you grab the bottle, right, and you introduce some kinetic energy, it gets that extra lift to, you know, make the change in state. Another example would be this. when you hold ice on your hand, when you take ice on your put it on your hand, right? The water that melts, is it the same temperature as your skin, or is it cold?
It's still cold, sir.
Still cold.
No, cool.
It's still cold. So at the exact point in time where the the ice melts to liquid water, what do you suppose the temperature of that water is?
0 degrees Celsius.
Zero.
As you say,
0 degrees Celsius. So as you could see, it's changing state from a solid to a liquid, and there's no change in temperature.
so
Once it's a liquid, it'll start absorbing the heat from your skin, and it'll start to change temperature.
it come like when you have a hot cup of tea, right? And you're using ice cubes to melt it, but like when you put the ice in the tea, like it melting, but there's no temperature change.
You gotta
only
wait for the ice
it's only
to.
like
You gotta wait
after
for the. Yeah, yeah.
it's only like after a particular while, the melted cold water would gain heat energy from the hot. You know what I mean?
That's a perfect example.
Yeah.
Because, guys, think about it. When you put an ice cube in a hot cup of tea, will the ice melt to turn into that hot water immediately, or will it, or okay, when it melts, right? It turns to cold water, and then that cold water will absorb the heat from the hot tea, and that will lower the temperature. You
Yeah.
understand?
Yeah,
So
that makes sense.
it's a little process. It's a little process. Right? So we would see happening is that so Kelani, you would have specific latent heat of fusion. So the you'd have to calculate, well, first of all, yeah, the ice would have to turn to liquid water first. So you'd use specific latent heat of fusion. And when it is water, then it would start to gain heat from the hot cup of tea. And then you would use specific heat capacity to calculate that energy there. But it's a two-part process.
Now I understand what you're talking about now, sir.
So the
So Nick,
the how to say it, but it's like the I know I want to say it, but I just want the right words come out. The heat gained by the water,
the
sir.
yeah,
Yeah.
the heat
The
gained
heat
by
gained by the
the
water equals the energy, or the heat loss, or the temperature
yes,
loss by the you know what I'm
yes.
trying to say? I know I
The
know what I'm
heat,
trying to say.
yeah. So the energy gained by the the ice water is the same energy lost from the tea, and
Yeah.
that would generally lower
You
down the
still
temperature.
Yeah.
that's being
Yeah,
live stream, right?
yeah. This being live stream on YouTube, I believe.
Okay.
Right.
So I have
So
to go
cool.
back and see where I miss. All right.
Right. So when we talk about units here, let's think about it logically. Of course, we're dealing with energy, so that'll be joules. And what else am I dealing with?
Massive.
I'm dealing with mass. So if I told you that my units are joules per kg, are you going to look at me like a madman, or that makes sense?
Nah, that makes sense.
That makes
That makes
sense.
sense.
That makes sense, right? Because it's joules per kg. Let's look at specific latent heat of vaporization now,
That is liquid to gas,
or vice versa. Yeah.
or vice versa. Without a
And what would
change
we
in
use to
temperature.
represent this? What would we use to represent this?
LV.
Joules
Well,
per
that'd be-
kg.
We use LV, right? We use LV. LV.
Yeah.
So here what? I just got and copy and paste, guys, because it's like more or less the same definition for this, more or less.
Yeah.
So, I thought you was talking about when it wasn't changed. I understand that you was talking about it wasn't changing in temperature when it was converting from one form to the other.
Wait, memorize this quickly. Yeah, some of that again, Nikolai.
So what I understand from this is it's when it's the specific latent heat of fusion and vaporization is when it's not changing temperature, when it changing states. It's like
Yes.
Solid to liquid. Okay.
So, and when, okay, let me explain this at a deeper level, right? Let's just, so Nikolai, at what temperature does water turn to steam?
Water turned to steam.
Yeah.
0?
Nah, at 0 degrees it turns to ice.
Oh. So. Oh, my bad.
100 degrees, 100 degrees Celsius. Now, the
Okay.
water, the water would have to reach 100 degrees Celsius first. But let me ask you a question, Nikolai. Do you think the structure for a liquid and a gas is the same?
No.
No. So here's what has to happen. The water first has to experience a change in temperature and it has to reach 100 degrees Celsius. You with me?
Yes, sir.
Now, at that point in time, it's going to have the atomic structure of a liquid still. Now, it's at 100 degrees Celsius, so it's really, really close to becoming steam. The only thing that has to happen again is you need some extra energy to break the bonds, so it turn to the atomic structure of a gas. So that extra energy you need to break the bonds or form the bonds is really latent heat of fusion and latent heat of vaporization. Hope you understand that.
Yes, sir, I understand. It's just all of this how to remember now and answer. Bring it back.
All right. So you guys understand what I'm saying, right? Like it had to reach like the turning, like it had to reach the boiling point or like the freezing point, and then you'll have the latent heat of fusion, latent heat of vaporization, and then it will make the change, the conversion to the different state,
Is that process, yeah.
that
Yes, sir.
process. So we use these two anytime we're dealing with a change in what? A change in what?
State.
And when you're changing state, is there a change in temperature?
No, sir.
No, sir.
No, sir.
Again, if you are somebody that's confused, imagine holding ice. When the ice melts, is the water cold or is it just magically the same temperature as your hand?
Cold.
Cold.
The ice is cold. And so the immediate point in which the ice freezes, the water is 0 degrees Celsius. So I hope that makes sense. It changed from a solid to a liquid, but the temperature remained the same. When the ice touched your hand gave it enough energy to break the bonds and become a liquid. But the liquid is still at the same temperature, 0 degrees Celsius. It's only when it's a liquid now is the temperature going to start to rise. So I hope that makes sense.
Yes, sir.
Let me look at the kinetic theory of matter now. Could anybody tell me the kinetic theory of matter?
All particles are in
Excuse me,
constant
sir.
motion.
Can I take a screenshot, please?
Wait, you in the group chat?
Yes, sir.
All right, I can send these notes immediately after this.
Okay, thank you.
Yeah, no problem. I'll send these notes immediately after. So does anybody know what the kinetic theory of matter says?
All particles are in constant motion.
You're not wrong, but you had to be more specific. So you had to say how all matter is
Has
made up of particles
particles.
in random motion.
Oh, okay.
Of particles in right?
So can I also say this? Kinetic theory of matter explains the behavior matter in terms of motion of tiny particles, atoms or molecules.
Yeah, that's fine.
Okay.
So question. I'm telling you that matter is made up of particles that is in random motion. If I add energy to the particles, are they going to move faster or are they going to slow down?
Move faster.
Faster, sir.
Good.
Faster.
So adding energy, what is adding energy to?
It
Adding
caused
energy,
the molecules to move more rapidly.
Yep.
And it breaks bonds.
Yep.
Gives them more energy. Well,
Particles
basically.
move more vigorously. See? All right, so adding energy makes the particles move more vigorously and further apart. So let me explain something quickly. So let's just say we have a solid here, right? Now, if we're talking about the atomic structure of a solid, the what would the structure look like? Would the particles, well, would the molecules be like very loose, or would they be like very packed and rigid?
Very
Packed
packed.
and rigid.
Packed, sir.
Will be packed and
Very
rigid.
packed.
Yeah, so the particles are like really, really close together. And would you say that the bonds are weak or strong?
Strong.
Strong bonds.
And strong bonds. Because you need strong bonds to hold all together.
Correct. So what would you guys say this is representative of? A solid, liquid, or a gas?
Solid.
A solid.
Solid, sir.
Solid.
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 Yeah.
This is a solid. Are the particles vibrating very, very rapidly, and are they vibrating a lot?
No. They
No.
vibrate, but not a lot.
Let's just say we add a lot of heat to this. We add a lot of heat to this. What's going to happen to the molecules here?
They're going to start to separate.
Vigorously and break bonds.
Yes.
Exactly. And let me ask you a question, right? This is a perfect example. So, as you could see, we have a given volume. Well, this is our 2D surface. We have a given area over here, right? Now, when I apply heat for a prolonged period of time, wouldn't these molecules want to start to vibrate? Wouldn't they? Okay, let's explain what's going to happen. The heat energy, the particles are going to receive heat energy, and that heat energy is going to be converted to what type of energy?
Kinetic energy.
Kinetic energy.
Kinetic
Right.
energy.
Anytime you have particles in motion, you're dealing with kinetic energy. Kinetic energy is the energy particles or a body possesses as a result of motion. So applying heat energy, and the particles are going to gain this kinetic energy, and they're going to start to vibrate more vigorously. And if they're vibrating more vigorously, wouldn't the bonds weaken and they would want to go further apart?
Yeah.
Yes.
Yes, sir.
Do you think this area is going to remain the same?
No,
No,
sir.
sir.
No. They're going to vibrate, and they're going to start to push against the walls. And if they're pushing against the walls, this area would what?
It would, well, break bonds.
Break
No,
bonds.
okay. This square over here would it remain the same size, or would it increase?
No,
would
sir.
It will increase. It will increase.
That's what I meant for.
Will increase.
So these molecules over here are going to start to vibrate more vigorously, and they're going to want to move apart, and they're going to push against the walls. And as you can see, this is increasing the area, and consequently, it would increase the what? If area is increasing, what would increase as well?
Would it be the volume?
Yes. Odd maths people. Or they should know, like, it have some formulas where they would ask you to find the rate of change of the volume with respect to the area. So you might have to find dVdA, and you got to use rates of change.
Yes, sir.
That's our application of this. So you understand that when you apply heat to a substance, kinetic theory of matter says that the particles are going to gain kinetic energy, and they're going to start to vibrate more vigorously. Bonds may be broken, and they will move further apart.
Yeah.
Yes, sir.
Okay, so this is a solid. What state does this look like?
Liquid.
Liquid.
Yeah, this looks like a liquid.
Liquid.
This looks like a liquid, because in a liquid, the molecules still kind of close together. They could move freely, they could move a bit freely, but they're still kind of close together, right? Until you see now, they're still kind of close together. Some of them kind of close together.
Yes, sir.
Yeah.
Yes, sir. Sir, I
Yeah.
have an actual live model in front of me, so
Hey, you can show me the model.
Sure, no problem. It's not mine
Yeah.
though, it's mommy own, but at the
Oh,
train.
okay. Yeah, you can show you. So we just looked at the main things: specific heat capacity, latent heat of fusion, latent heat of vaporization, and kinetic theory of matter. How are you feeling so far with the basics?
Yeah, good.
Feeling
Good. Okay. I wonder if it have anybody on YouTube, buddy.
Hello.
It has 76 people on YouTube. That's shocking. I wasn't expecting anybody to be on YouTube, buddy.
Hold on, man.
Excuse my hair, not keeping my camera on for long, but still, this is
We not
this gas. Just now. Camera again, trouble. Hold on.
all right. We gotta move on. We gotta move on. We gotta move on.
Right.
Really. All right. Show it fast.
There's gas.
Oh, okay, okay. That's cool.
Yeah.
That's cool.
Cooler.
All right. So let me continue. All right. So they want to do a question one time.
Sure.
Yeah.
All right. Complete table 3 by inserting the correct symbol and SI unit which relates to the quantity shown in column 1. So specific heat capacity, we have to say the SI units. What are the SI units? Oh, by the way, guys, if we are dealing with SI wait, I have a question, right? If we're dealing with SI units, am I going to write joule per kg degree Celsius?
no, sir. Use
No,
Kelvin.
sir.
No, I'm
Isn't
not
when
gonna
they say
put
SI unit, they mean the symbol that represents it? Like the
Nah.
lowercase j or something?
Yeah, so like when they say SI units, they're talking about the fundamental units. So like
So like Kelvin and them things.
yeah. So here what, guys, I'm gonna quiz you guys, all right? So tell me, what is the SI unit of mass?
kg.
KG, sir.
Round.
kg, kilograms.
Kilogram, not grams, they're kilograms. What is the SI unit of current?
Amperes.
Amperes,
Amperes.
yeah.
Amperes, right?
Capital
S-
A.
what is the SI unit for length?
Meters.
Meters.
Sorry.
Meters.
What did I say, boy?
What is the SI unit for temperature?
K.
Kelvin.
Kelvin, capital K.
Not degrees Celsius earlier. Not degrees Celsius. Not degrees Celsius. What about for light intensity? I don't think all might know this one.
Candela.
Nah, I don't know.
Candela.
The last something.
And how do you represent candelas?
CD.
CD.
Oh, CD.
CD.
Right?
The C is capital C and the D is lowercase d. CD.
Yeah. What about sound level?
I know that one, sir.
Sound
Decibel.
level.
Decibels.
That's the, oh, well, I didn't know about that one.
I know when I never remember that.
All right. Are there any other ones that I could tell you guys?
Amount of substance.
Onto substance.
Wait, another one I could tell you is pressure. What's the SI unit for pressure?
PA, Pascal.
Pascal.
Pascals.
Pascal.
Okay.
Pascal.
Cool. Right. So if we're talking about specific heat capacity, it's gonna be joules per kg. What? Degrees Celsius or Kelvin?
K.
Kelvin. Per Kelvin.
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 Even though
Capital.
degrees Celsius is correct, they said SI units, so we have to put Kelvin. Specific latent heat of vaporization. What I put for that?
LV.
LV.
Right? LV. And
Specific latent heat.
and where's the SI unit for that? Where's the SI unit for that?
Joules per kilogram.
Joules per kilogram.
Okay.
Cool.
Kel.
Joules per
and
kilogram.
And this makes a lot of sense because this one, there's no change in temperature. So would I put Kelvin?
Nah.
No,
No,
sir.
so once it has no change in temperature, you must never put Kelvin. It will
Exactly.
just be joules per kilogram.
Right? Heat capacity of a substance, what's that?
The amount of
Energy.
energy required to
The amount
change
of energy required.
temperature of a substance by 1 Kelvin or degree Celsius.
Yes, so
Cool.
what she said.
I feel lazy to write that back, so I just gonna copy and paste. But yeah, just waste it. That's fine. All right, write the equation that relates specific heat capacity with heat capacity. Liam, if you're here, I want you to answer this question. I guess Liam not here. Anybody want to tell me?
So,
MC delta theta.
Nah, heat capacity and specific heat capacity. Capital C is equal to what?
MC.
Oh, MC.
Yeah. Remember, capital C is heat capacity, and common C is specific heat capacity, right?
Oh, so okay.
Yeah.
So
So
what is the other one?
specific heat capacity is common C, and heat capacity is capital C.
Oh,
Okay, so
okay.
like maybe in one question they might ask you to find the specific heat capacity, and the next question they might be like, okay, given that the mass is 5 kilograms, find the heat capacity. So you just multiply the specific heat capacity by the mass.
Oh, I see, I see. Thank you, sir.
No problem. Who wants to
So
do this
you
question?
send it in the group chat too?
Yes, I will. Who wants to help me with this question? It's like a solid
I don't
example.
mind. Yes, sir, yes, sir, yes,
All
sir.
right. All right. So Nikolai, a busy housewife, left 25 grams of ice in an open insulated container while she was answering her cell phone. When she returned, the ice at 0 degrees Celsius was converted to water at 3 degrees Celsius. Calculate the energy needed for the ice to totally melt and to reach its present temperature. Assume no heat losses. So Nikolai, when you read this question, you see that they want us to calculate the energy.
So,
And it's a two-part process because they said needed for what?
for the ice to totally melt.
Right. If the ice is melting, what am I doing there? If the ice is melting, is that E is equal to MC delta theta? Or is that something else?
That's something else we
So,
didn't with the paper.
oh, I supposed to write the formulas here earlier. This one will be E is equal to MLV, right? E is equal to MLV. And what this one will be?
E is equal to MLV.
MLF.
MLF.
Because this
Oh,
one is
my bad, my bad.
wait, wait in the wrong space. That don't be. Alright, so cool. So Nikolai, what doing? But I feel like I passed the question.
Yeah,
Yeah.
you can pass it.
So if we're talking about totally melt, if we're talking about melting, that's a change in what?
A change in state.
Good. Change in state. Which formula would you use for this?
Fusion.
Right. So I'd say E is
From
equal to
solid to
ML.
F.
All right. Cool. And then they're saying to reach its present temperature. If it's reaching a new temperature, then that implies a change in what?
A change in the temperature.
Correct. Because originally the ice would be at 0 degrees Celsius. So let's write the process down. So Nikolai, we would have started with ice over here. And what's the temperature of the ice initially?
Was at 0 degrees.
Okay, and then this would have turned to what?
Would have turned to water.
Water at what temperature?
3.0 degrees Celsius.
Ah, let's see that. Let's see that. Let's see what happened just now there.
What?
Nikolai, talk to me, right? Imagine what you say. Yo, if you could go in the kitchen right now and get a cube of ice, right? Nikolai, when you put ice block on your hand, right, Nikolai?
Yes, sir.
I can't stop share for this one. I had to see the emphasis on my face. So, wait a all right, so let's see it, right? Let's see it, man.
Yes, sir.
When you put an ice block on your hand, when the ice block melts, Nikolai, is the water that melts cool or the same temperature as your hand?
It will be cold.
You say that like you was unsure. I really feel you had to get a block of ice and put it on your hand, you know. But Nikolai, if Okay, Nikolai, when you put the ice block on your hand and you touch the water that melts from the ice, is it hot or is it cold?
It's cold.
And after some time passes, that water eventually becomes
Heated because of your hand.
exactly. So, Nikolai, you just told me ice goes immediately to water at 3 degrees Celsius. Is that true?
Oh no, no.
No. When the ice melts, it's gonna turn to water at
0 degrees? Because
yes, yes, yes.
okay, yeah. No, I understand. Yeah, okay.
That's the mistake everybody does make, you know. That's the mistake every.
Daryl.
Question, sir. What past
Daryl mind
paper?
twister.
So one question. What past paper is this? If I
This
want to
is
you
2011. This is 2017 June, I think. I'm not sure. I'm not sure. I just about to run. It's a random compilation.
alright, sir.
So the ice at 0 degrees Celsius would have turned to water at,
0 degrees.
and after it turned to
Excuse me.
water, wait, after it turned to water, what would happen then, Nikolai? What would happen next?
Change temperature.
I wonder if I wonder if people on YouTube get in this way. Right, people on YouTube getting it nice. Yeah. So eventually, this water would heat up to what? What temperature?
3 degrees. Well, 3.0.
Right. Like right tree. That's fine. Yeah, Renisha was asking my question.
So I remember this question. I think it was from last year, May, June. Is that correct?
Yeah. This is the same document. This is like a good compilation. If it
Okay.
then broke, if it then broke, I don't mess with it. This is a really good compilation I would make. So
Well,
Nikolai,
thanks for doing it over, because in the exam last year, I didn't quite understand what to. So
no problem. So Nikolai, from here to here, there's no change in temperature. What formula I would use?
The fusion, latent heat of
Right.
fusion.
So I'd say E is equal to M what?
LF. Well,
Okay,
I don't know how you
and
say the F. If it's supposed to be a regular F.
that's fine. It's a common F. It's like a really small F. It's a really small F. Right? And Nikolai, is there a change in state there?
No.
No, but there is a change in?
Temperature.
Right. So over here, I would use which formula?
Heat capacity. No, specific heat capacity.
Right. So I'd say E is equal to MC. Wait,
Theta. Theta.
yeah, delta theta. Cool. Now, I know for a fact somehow they're gonna use M as 25. I know that's correct or that's wrong.
No, I had to convert it.
No, because initially I
I
had to calculate
I
for
think
the
you're
energy.
supposed to convert it.
Nikolai, we just talk about SI units. Is grams the SI unit for mass?
No, sir.
No. So I have to convert 25 grams to what?
Kilograms, sir.
So what I gotta do?
Divide by 1,000.
Divide by 1,000. If I divide 25 by 1,000, what that will be?
That will be 0.025.
0.025,
Yes, sir.
right? I'm gonna just confirm the 1, 2, 3. Yeah. I'll confirm that's correct, right?
Yes, sir.
Yeah.
Yeah, that's
Yes.
correct. All right, cool. So Nikolai, let me begin, right? So E is equal to MLF. What is the mass?
0.025.
Okay, what is the latent? What is the specific latent heat of fusion ice?
That very big number.
Right? 300.
340,000.
And if you guys notice, look at the units, or look at the units. It is joule per Kelvin. I mean, what's it, per kilogram, right? kg to the power -1 means over, like joules over kg. Add maths people, you should know a negative power implies a fraction, right? kg to the power -1 actually means 1 over kg. Did you guys know that or no?
Yes, sir.
Okay, that is negative power rule.
Yes,
Sir.
sir.
I know doing this.
Right. All right, multiply this on, let me know what you guys get.
8,500
8,500.
joules per kilogram.
No. That's joules.
Yeah,
Let me explain something, Kelani. Let me explain something. Look at
Because it's
look,
energy.
yeah, a lot of students don't realize this ever. Watch something, Kelani. We're multiplying mass by specific latent heat of fusion. What do we measure mass in?
kg, sir.
And we're multiplying that by specific latent heat of fusion, which units are joules kg to power negative 1. That's really kg multiplied by joules over kg. So what would happen to the kg?
Cancel out.
To leave you with?
Joules.
Yeah.
Yeah, and plus energy is in joules, so that's how you know too.
Yep. I love physics, you know. Physics real bad. Physics real bad. Right? People on YouTube, let me know if you understand that. People on YouTube, let me know if you go with that. People on YouTube, will you understand that? Or nah? YouTube people. Okay, I take it that they understand. Nikolai. So we calculated the energy it would take to convert the ice to water. Now, when you have water, the water is now going to start to gain the heat from the surroundings. And there's a change in temperature. So we use the other formula. E is equal to mc delta theta. Right? So Nikolai, what was the mass?
the mass was 0.025.
What is the specific heat capacity of water?
4,200.
And what was the change in temperature? We went from 0 to 3.
So it'll just be 3 minus 0, but it will still be 3.
That'll be 3, right? If you want to get for the full thing, I suppose 3 minus 0. Alright, let me know what you guys get. I trust you know to be fast with this, you know. Quick, quick, quick.
I have 315.
315.
Yes,
All
sir.
again, 315?
Yes, sir.
Yes,
Joules.
sir.
That's supposed to be in joules.
Yeah, that should be in
Joules?
June.
Energy.
So, if we want to find the total energy, which is ET, how are we doing that?
Minus the energy from
Nah,
the
nah, not,
Add them
not
together.
minus.
You have to
Not
add the two.
Nikolai. Hey, Nikolai, you had to explain to me why you say mine. I'm not judging you, no, Nikolai, but I'm curious as to your reasoning. Because here, what, Nikolai? How much energy it take we to go from ice to water?
8,500.
How much energy it take we to go from water at 0 to water at 3?
Oh, my bad, my bad. I now see why I make that mistake. It's supposed to be 315.
So all together, to go from ice to
Ah,
water
it's
at 3
added.
degrees, you gotta add. Hope
So I
that
don't know
makes
where
sense.
to get the minus from. Probably, I don't know. Nah, I don't know.
Yeah, I don't know like that. Gotta be careful. So it could be 8,815 joules. I'm gonna follow you okay with that.
Yes, sir.
Or so
Okay, cool. That was easy or hard?
Not too
It
bad.
was, I find this
simple.
question real nice. I want to go back and try it for
The way
myself.
how you portray it, it seemed very easy, but in the time of pressure, when I had to do this question, it was like, what the hell I was doing? What the hell I was doing, Renisha? What the hell I was doing?
Whoa, language, language. But I wouldn't say
Sorry.
these questions is light work, easy marks. So Nikolai, now you know ice don't just go to water at some temperature. It has to go to water at 0 degrees Celsius, and then when it's water, it can then gain heat. Yeah,
Yeah, so 6
So,
marks.
hey, sir,
Real
you,
marks, boy.
sir, you're
that's why I
bad,
say
you're
it.
bad, you're bad. Because you see how you explain it there? Nah,
Yeah.
my teacher didn't explain it like that how you do that there, sir.
A lot of physics teachers just tell children to learn the procedure. They don't explain why it does work. And so students will gain an intuition for it. Right? So Nikolai, read part 2 for me.
If this melting and heating activity took over 300 seconds, calculate the rate at which ice slash water was receiving heat.
All right.
Was that? Wait. Okay.
Better. So you have to know the formula for power here. Do you guys know the formula for power?
Yeah.
Yes.
Well, power
Well,
is
You divided by time.
Say that again?
Is that energy divided by time?
Yes, and I can show you a legendary way to never forget it. Let me blow all your mind, right? So Nikolai, they're telling us that the melting and heating activity took place over 300 seconds, right, Nikolai?
Yes, sir.
So, Nikolai, in 300 seconds, how much energy was supplied to go from ice to 3 degrees Celsius water?
8,815.
Right, so in 300 seconds, 8,815 joules of energy was delivered, right?
Yes, sir.
So we want to attack this from our AdMaths perspective. So they're saying calculate the rate at which the ice water was receiving heat. So anytime you see rate, you know you're talking about time. Is that not true?
Yes, sir.
And water receiving heat. When we're talking about heat, we're talking about what there? Heat is a form of what? Heat is a form of what? No, heat is a form of what?
Temperature.
No, energy.
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 Nikolai, this 8,815 joules, this is heat energy, you know. This is heat energy, my guy. This is heat energy, you know that, right? Or not?
Yes, sir. Yes, sir. Is
Well,
this
I
why
hope you know that. So if we were to attack this from an AdMaths perspective, wouldn't this be what would it be? The change in what with respect to the change in what?
It'd be the R at the top with respect
Nah,
to
it
time.
could be DE dt.
Oh,
DE
DE.
dt.
Yeah, DDT. I was
Good.
thinking DRDT. Oh, my bad. No.
So they want me to figure out. I'll go see where I'm going with this, right? I want you all to stop thinking about physics as just formulas. Try to understand it at a deeper level, right? It's not a time to understand it at a deeper level. So the change in energy with respect to time. So if I wanted to find that, let me show you something bad, right? Just from this alone, I could say 8815 over 300 and I'll get my answer. I'll get my answer one time. Isn't that what the formula does do? Isn't that the formula for power? Power is energy over time.
Yeah.
Yes, sir.
Didn't they want us to find the rate of change of, well, they wanted us to find the change in energy with respect to time, which is the definition of power, which is 8,815 over 300. And just like that, you was able to derive that and figure it out in the exam without memorizing any formula. So I just thought I'd show you that. And you can apply where you learn in AdMaths. And just like that, you'll get the answer here. Now, if you want, you could use the formula for power. Power is just simply energy over time. Now, energy, we find the energy above. That was 8,815. And what was the time?
300 seconds.
300. Right. Now, I know not everybody is doing AdMaths. That's why I'm showing the AdMaths students this as well, because they deserve to see the correlation and the linkage. And the people are not doing AdMaths, the formula right here, P is equal to E over T. This is the formula you would use, right? I'll leave it. I'll just leave it here. This is like, you should know. Yeah, so AdMaths people, you know, the way you learn AdMaths is utilizing physics a lot. So let me run through the question again. They wanted us to find the rate at which the water or ice was receiving heat. So what they really want us to figure out there is power. And how do I know that, guys? How do I know that? Well, again, look at what they want you to find. Guys, they want us to find the rate. When we talk about rate, we're dealing with time at which the ice water was receiving heat. They're talking about energy. So what they're really talking about is energy over time, which is what? What's energy over time?
Power.
Power. And so when I calculate this, what is going to be my units?
28.38. Oh,
The
units?
units are gonna be joules at a time top, and time would be seconds, so joules per second.
You're not wrong, but we're going to write watts
What?
because the
Oh,
units of
watt.
power is
Yeah.
watts.
Oh yeah.
Yeah.
So I got
Sir, so if you
28.38.
wrote the derived unit, would you get that wrong?
I don't think you're getting marked, you know. I don't think that's what they want to see. They want to see watts. They
Okay,
want to
sir.
see watts. I'm gonna work this out quickly. Yeah, I'm getting 29.38.
So that's why I get to.
Okay,
I'm
nice.
using the
So I'm going,
scientific calculator on my phone.
okay, good. So I'm going to explain this again so that you all will understand what the question is asking, because I understand a lot of you guys don't. How much of you guys would have known you had to calculate power here? Be honest with me. People on YouTube, how much of you guys would have known you had to use power here? I guess a lot of you guys would not know that. So let me try to explain the question again. They're telling us the melting and heating activity took place over what time, Nikolai? Over what time?
300 seconds.
Right. So in that time, how much energy was supplied?
The 8,815 joules.
Good. So they want us to calculate the rate. Anytime you see rate, we're talking about how something is changing with respect to time. What is changing with respect to time? They said the ice / water receiving heat. So they really want us to figure out how the energy is changing with respect to time. So they want us to find E over T, which we know that is what? Power. Right. So anytime you see rates at which something is receiving heat, just know they're talking about power, because they're talking about the rate at which something receives energy. And the rate at which something receives energy is power. Power is just energy over time. So, okay, people on YouTube, people in the Zoom, hear what? If you still don't understand, what did they make us find in the last question? Somebody tell me, what did they make us find in the last question?
The total energy from the ice and the water.
Right. Total energy. People on YouTube, people in the Zoom, they wanted us to find energy. Energy, right? And in this question, what they give we?
Time.
The time, sir.
Time. They give we time. People on YouTube, on Zoom. In the last question, they give we energy. In this question, they give we time. What formula we know have energy and time in it?
Power.
Power.
Power is equal to energy over time. That's the simplest way I could tell you. You're looking for what they give you, and they're using that as a guide. So, like, if you're really confused, just know in the last question, you found energy. And in this question, they're giving you time. The only formula that comes to mind with these two variables is power. Power is energy over time. And it's measured in watts. That's like that's the only other way I could explain that to you guys. All right. Are you okay with it?
Yes, sir.
Yes, sir.
Yeah.
You see these types of questions, these calculation questions, I could do a whole physics exam with just calculation questions. I hate them questions where you had to explain thing and you know put like definition. I don't like them thing. I don't like them thing. All right, so let me move on to another type of question.
Yes, sir. Sir, there was one with a kettle. Like the power of the
Kettle.
kettle. Yeah.
Well, I will look for the question and we go do it.
Yes, sir.
All right. So you guys have to know what the greenhouse effect is. All right, so I want to let you gain our intuition for this. So okay, all if you like the sun just produce a little bit of energy or a lot of energy?
A lot.
A lot.
Right.
I know.
Right. So what do you call wavelengths that have a lot of energy? Would you say so? Okay, we understand that the sun is a lot of energy. A lot of energy.
Long wavelengths.
Nah.
Short wavelength.
When you guys do unit 1 physics, you guys will learn about Planck's equation, and you'll see it's relating energy, Planck's constant, and frequency. Now, I'm not sure if you guys know this, but V is equal to F lambda. And so if you were to make F the subject of the formula, you'd get V over lambda, right? The velocity of all electromagnetic waves are what? If we're talking about electromagnetic, something is in the electromagnetic spectrum. Everything in the EM spectrum travels at what speed?
Light speed.
Light speed. Once it's in the EM spectrum, remember, rich men in Vegas use expensive gadgets, radio waves.
Yeah.
Okay, good. So if I'm talking about EM waves, I will replace velocity for c, which is the speed of light, and I can plug it in here. So this is the relationship linking energy, Planck's constant, and the speed and the wavelength. So let me ask you a question, right? Let me ask you a question. If I have plenty energy, do you think my wavelength will be big or small?
Small.
Small, sir.
Small. Small,
Small.
because it's in the denominator. If I want a large answer, would I want a big denominator or a small denominator?
Big.
Oh, small.
Small.
Small. Okay, what would be bigger? A half or 1/1000?
A half.
Half.
Uh-huh.
Definitely a half. So here we're saying, guys, if you're doing Unit 1 physics, you learn about Planck's constant and this relationship. I'm just giving you a preview. So from this, guys, if something has high energy, do you think the wavelength would be small or big?
Small.
Small, sir.
Small. So we understand that the sun gives a lot of energy. If it's given a lot of energy, then the wavelength of the EM waves it's given off, it's going to be what? Short or long?
Short.
Short.
Short. So the sun is emitting short wavelength radiation. And we understand the smaller the wavelength, the greater the energy, right? And the sun produces a lot of energy. So the sun is going to give off short wavelength radiation in the form of IR waves. If we're talking about penetrative ability, like its ability to go through glass or whatnot, would you say the sun has a high penetrative ability or low penetrative ability?
Low.
High penetrative
What?
ability.
Repeat that, sir?
Nikolai, does the sun emit low energy waves or high energy waves?
High.
Do you think that would have a hard time passing through something like glass?
No. Oh, no.
No. Okay, if you're confused, guys, if you leave your car in the sun and you come back like an hour after, will the inside of your car be hot or cold?
Hot.
Hot.
Too hot.
Hot.
Hot. So Ollie, tell me, right? Does the sun have a hard time? Does the sun rays, well, the IR waves from the sun have a hard time passing through glass?
No, sir.
No.
No, sir.
No.
No. So the short wavelength radiation from the sun has a high penetrative ability. So again, guys, do you think the short wavelength radiation from the sun, do you think it has a hard time passing through glass?
No.
No, sir.
No, it does. No, it does
So
not.
because
No, it does not.
no. Mhm.
Say that again. Somebody was saying something.
She said something about the glass.
Well, the short wavelength radiation could pass through the glass. But let me ask you a question. When the short wavelength radiation enters the car, it's going to be absorbed by the heat and the plastic inside the car. A little bit more now.
Yes.
Sir.
Okay, so
Yes, sir. There's a reason for that because black surface it's good heat
yeah,
absorbers, but bad they are good heat absorbers, but bad it's a little comment
Emitters.
out, but you know what?
Emitters. I
Yeah.
think she's trying to
okay.
say emitters.
Black, no. Black surfaces are excellent emitters. I know it's a bit
Okay.
counterintuitive, but black surfaces are excellent emitters. I have everything you need to know somewhere over here. If we're talking about black surfaces are very poor reflectors.
It's a the
That's what
shiny
they
surface and it's a the dull surface.
Reflect. Oh, sir, I really mixing up thing, you know, sir. Hey.
Don't worry. After today, you go understand. But anyways, let me get back on track. The wavelengths, okay, the sun rays are gonna easily pass through glass, and that's going to be absorbed by the seats and whatever. Now let me ask you a question. When you heat up the seats and whatnot, that is going to re-emit heat. What's gonna emit more heat? The sun or like the heated up car seats?
The sun?
Heated up car.
The sun is isn't the sun where the heat coming from?
Yeah.
Oh, yes.
Yeah.
Yeah. So like the sun gives us a lot of energy. Now the sun is going to heat up the things in the car. when you heat up the things in the car, and if you heat up something, right, wouldn't that emit some heat?
Yes, sir.
Yeah.
Yes.
Guys,
No wonder why inside the car be so hot.
right, stay with me, right? If I heat a pan, and if you put your hand close by it, and you go feel some heat emitting,
Yes,
Yeah.
sir.
Yes.
okay, is it a large amount of heat compared to like with direct contact, or is it like less heat?
Less.
Oh, it's less heat.
It's
It's
less
not
heat.
really touching you, but you're feeling it going on your hand.
Right, but like, okay, if I'm a feet away from it, am I feeling that heat energy or not?
No.
Nah, not really,
No, you
not really,
wouldn't
right?
feel it.
Nah, I wouldn't feel it. So here what happening? The sun is easily gonna pass through the glass. It's gonna heat up everything inside the car, but when you heat up the seat and thing, is the seat gonna be able to emit that heat as effectively as the sun?
No.
No, sir.
No, it's not. So let me answer that question. When the seats and everything absorb the heat, they're gonna have a hard time emitting that heat. So it's gonna turn to long wavelength radiation. And do you think the long wavelength radiation could exit now?
No, sir.
No, sir.
No, it can't exit. So you know what happens? Over time, everything inside the car becomes heated because when the sun heats up the seats, the heat emitted by the seats, they are long wavelength radiation, but that can't escape through the glass. So where does it get trapped? Where does it get trapped?
Inside the car.
It's in the car.
Inside the
Inside
car.
car.
Set the car.
And so that is the whole process of the greenhouse effect. That's the whole process. So
it's staying in the car, so it will get cool over time.
no, hot. Let me look at the example over here, right? So from the sun, we're going to receive short wavelength radiation, which are IR waves, and it has a high penetrative ability and it's high energy. Over here, we have a glass, we have a black collector plate, and we have copper tubes. By the way, this is a solar water heater for those that didn't know. So, question, guys, isn't the short wavelength radiation gonna enter easily?
Yes, sir.
Yeah.
Yes, sir.
Yes, sir.
It's gonna enter easily, and it's gonna heat up the what?
The black collector plate.
Good. It's gonna heat up the black collector plate. Now, what is hotter? The surface of the sun or the surface of the black collector plate?
Surface of the sun.
That's the
So it's
sun.
not.
Exactly. So, do you think the black collector plate is gonna emit as much heat energy as the sun?
No,
No.
sir.
No,
So, okay, when the black collector plate gets hot, it's gonna start to emit energy. But is the energy gonna be enough to escape through the glass?
No,
no,
sir.
sir.
No, it's not going to be enough to escape the glass. And so it's going to emit long wavelength radiation, which cannot escape because it's low energy and it gets trapped. So that's the whole process of the greenhouse effect. Whole process. So let me put it in words for you now so you can understand it. So look, have a good example here. Have a good example. So short wavelength IR light from the sun passes through the glass. Everything in the greenhouse absorbs short wavelength IR light and becomes warmer. Wouldn't the sun heat up everything on the inside?
Yeah.
Yes.
Yes, sir.
Cool. Now the warmed objects will give off long wavelength IR light. Why am I saying this? Yes, it's gonna get heated up, but is it going to emit a lot of heat?
No, sir.
No.
No.
No, it's going to trap, most of the heat is gonna be self-contained within. And so if it's emitting like weak levels of heat, is that re-emitted heat gonna be able to escape the glass?
No, sir.
No, sir.
No. So in turn, the glass absorbs the long wavelength IR and warms up. It gives off long wavelength IR, which mostly shines back into the greenhouse, and so therefore it can't escape. So let me give you guys a good answer. Let me put on a good answer. Right. So can anybody explain that to me?
Well, the sun produces short wavelengths that have high energy.
Right. So I could say short wave radiation from the sun passes easily through the what?
The glass
Medium or
with
glass.
high penetrating ability.
Correct. Passes easily through the glass and is in the context of this, right? And is absorbed by what?
By the black absorber. No, wait, what?
What was the
Was
name
it
of
the
it?
collector
And
plate?
it's
Black
right,
collector
and it's
plate.
absorbed by the
Electrified.
do not put black in capital letters. Cool. This would now become what? This becomes what?
After absorption, the black collector plate emits short wavelengths.
Okay, that's good. That's good, Nikolai. So the heat is going to be absorbed by the black collector plate, and therefore it become what? Cooler or hotter?
Hotter.
Right. So this becomes warm, but because it is much cooler,
Excuse me, one question. Would you say in that explanation that the black collector plate is a poor reflector but good absorber and emitter?
if you want, you could say that. You could say that, Nikolai. Yeah.
Okay.
But that's not the main thing you want to describe here. So this becomes warm, but because it is much cooler than the surface of the sun, right? Surface.
It produces long wavelengths. Oh, long wave radiation.
You had to talk about the re-emittance. So you would say it re-emits the energy as long wave. It's like a model answer. Eh? For radiation. So guys, again, I feel like this is logical, right? Which one will be hotter, the surface of the sun or the black collector plate?
Surface of the sun.
Surface of the sun.
Exactly. So the black collector plate, is it going to re-emit as much heat as the sun?
No, sir.
No, it's not. It's not. And if it re-emits less heat than the sun, obviously the energy it's emitting is going to be long wavelength and is not going to be able to escape the glass. So it's going to be trapped. So it re-emits the energy as long wave infrared radiation, right? And cooler objects always emits longer. And what would I say about the long wave radiation?
It ends
Can
up
the long,
trapped in the what is this, a container?
correct. So long wave radiation cannot escape through the glass. And what happens to it?
The copper tubes will take the heat that was inside the container.
Again, you're correct, but we don't want to talk about all that. We mainly want to talk about the greenhouse effect,
Ah,
right? Cannot escape through the glass, so it becomes trapped. Thus increasing the what?
the temperature inside the object.
Right, thus increasing the internal temperature. So do you guys understand the answer or no?
Yes,
I think
sir.
that
Right, so Kilani, read it from and let me know if you truly understand it.
All right, so when I asked you to this, before you describe the greenhouse effect, all right, so the shortwave radiation from the sun passes easily through the glass and it is absorbed by the black collector plate, right?
Wait, that you understand that part? Everything that makes sense?
Yeah, because since the sun emits a high level of energy, it isn't hard for it to pass through any medium, so it could pass through glass easily, right? So this becomes warm, right? So the black collector plate becomes warm, but because it is much cooler than the surface of the sun, it re-emits the energy as long-wave infrared radiation, right? That also makes sense because obviously the black collector plate isn't as hot compared to the surface area of the sun, right? And the cooler objects always emit longer wavelengths of radiation, right? Long wave radiation cannot escape through the glass, so it becomes trapped, thus increasing the internal temperature, right? So because the glass is kind of acting like a wall that traps the heat, right? It increases, as they said, the internal temperature, but still, even though the internal temperature is increased, it still wouldn't be as hot compared to the surface area of the sun.
I love how you say that last part.
That is a brief explanation of the greenhouse effect.
Yeah. Big up, big up, big up. People on YouTube. Let me know if you understand that. People on
Yes,
YouTube,
sir.
let me know if you understand that.
Big up Kalani, boy.
Kelani explain that real good, boy. Kelani explain that real good. Yeah. So I understand. The sun, real energy. Pass through the glass, no problem. It'll heat up everything inside, but it wouldn't be as hot as the sun. So it would emit the energy, it would emit long wavelength radiation, which cannot escape back. So like that long wavelength energy is gonna get trapped inside, and eventually that's gonna build up and it's gonna increase the internal temperature. That's the easiest thing. So like watch, real simple. The sun gonna give you short wavelength radiation. It's gonna pass through the glass. It's gonna heat up everything inside. The contents on the inside are gonna re-emit. It's gonna re-emit heat energy, but it's not hotter than the sun. So it's going to actually emit long wavelength radiation, which cannot escape the glass, and so it becomes trapped on the inside, and that's building up heat. That's a greenhouse effect. Um, a black collector plate is just like it could be like okay, it's real simple. It's just like a flat material that's painted black. That's all. It could be made out of some metal or something. So imagine you have a metal sheet and you paint the metal sheet black. Wouldn't this absorb heat very, very rapidly?
Yeah.
Yes, sir.
Yeah. So I should probably explain what's happening here. So over here you have a glass container. You have a black collector plate. The black collector plate is a good what?
Absorber.
Absorber of heat.
It's a
And
good absorber and good emitter. So when it absorbs the heat, it's going to emit the heat to the copper tubes that's in contact with it. And in the
it
copper
would
tubes, you're going to have water running through. And so by the time the water reaches over here, it would be hot or cool?
hot.
Hot. Right, hot. So I hope you understand that. Easy peasy lemon squeezy. Alright, so let me tackle this question. Any volunteers for this one?
Seeing that I do one already, I'll let somebody else go.
Okay, no problem. I feel like Kelani wants to do a question, you know.
Yeah.
I said, Kelani, give it a read.
All right. So the energy absorbed from the sun, the energy absorbed from the sun by a solar water heater is 300 kilojoules. Right. 35% of the energy is transferred to 1.5 kilograms of water in the pipes. Calculate the final temperature of the water if its initial temperature is 30 degrees. So so let's say, and normally when they say to calculate the final of something is like you had to take the initial and add it to another quantity, like another value to get the final,
Okay, you're thinking logically. Yeah. You're thinking logically.
right?
So which formula you think I should use here? Since I'm talking about a change in temperature. I'm talking about a change in temperature.
Well, we had a so looking at the E is equal to MC delta theta, you had to make the delta theta the subject of the formula.
Yep,
because it's a change in temperature.
correct. And once you have the change in temperature, you can then add that to the what?
The initial.
Big up. Kilani is our boss. He's our boss. He's our boss. Now, there's another way to attack the question, which is what I did. I didn't think about it like you. That's fine. I like your method a lot more. What I did was I replaced delta theta with T2 minus T1. That's what I did. And I just made T2 the subject of the formula.
And then you add it after.
No. Like, if you make T2 the subject of the formula, you get your answer one time.
Oh,
You just had to plug in everything.
oh.
I feel
So
like
keep
I
on.
might go more with Kalani's method, saying that I
Yeah,
wouldn't say that.
I understand. Yeah, Kilani's method is a bit better. I like. So, here what? They're telling us that you have 360 kilojoules of energy being absorbed. But outside of Kelani, what's the useful amount? What was the percentage we actually use?
Well, 35%.
So enter first must calculate the energy actually transferred to the water.
Yeah, you must do that first, yeah.
So let me find the E first. So to find the E, what I gotta do?
Find for E, you would have to put the 360 kg multiplied by the 35%, which is you can't obviously you can't write 35, you have to put 0.35, right?
Yeah. And wait,
Because
that kilo means is 360 multiplied by 10 to what power?
that's 1,000, so 10 to the power of 3. Yeah.
Right? And you'll multiply this by, so they said 35% is actually being utilized. So we're gonna multiply that by what? So 35% is what?
0.35.
Yep.
Yeah.
One question, sir. Couldn't you just subtract the 100 from the 35 and get that answer and then multiply by the 360?
Yep. Wait, actually,
Okay.
nah, Nikolai, nah, no. Nikolai.
A question
Oh,
I
wait,
asked.
wait. I think, say, Telma, you want to find 65% of the total and then take it away from the original amount. That's what you're saying. That would be
Yeah.
correct. But I feel like that's real working, Nikolai. Like, Nikolai, it don't want to be that complicated, you know. They're literally telling you 35% is used. So all you had to do, Nikolai, is just find 35% of that. That's all you had to do.
Okay.
Like, again, okay, if you're confused, I'm read it back again, right? They're saying 35% of the energy is transferred to the water. So 35% of this, that's all they had to find. 35% of that.
Okay.
Shivan, I see you have your hand raised.
So why multiply the 360 by 10 to the power 3?
I'm glad they asked that question. What are you seeing here?
Kilogram per joules?
Nah, that's kilojoules.
Kilo kilojoule, yeah, right. That.
Right, here what way to do, right? Take a screenshot of this from now.
And that's the prefixes, sir.
Yeah, they had on all their prefixes, man. They had on all their prefixes. Have to. They have to know all their prefixes. Take a screenshot of that fast.
Hey, look the manual, boy.
Emmanuel?
No, the manual, not like the physics manual.
Yes. This is Manuel well goated. Big up Sir Kevin Jared Hossain.
Yeah, I get that from KGH.
Yeah.
Big up.
Alright, I'll have the screenshot.
Yes.
Shivan.
I make a whole song with that, answer. But
Wait,
Yes, sir.
wait, let's
Yes,
see.
I understand
When?
why I want to buy the tune now, yeah.
Good. Hope you understand that. So we have kilojoules. Kilojoules means 10 to the power 3 joules. That is what it means. So 360 by 10 to the power 3 by 0.35. Why am I multiplying by 10 to the power 3? Because they're literally telling me kilojoules. So I need to convert it to joules. And they said only 35% was used. So I'm going to find 35% of this, which is represented by 0.35. So somebody plug this into your calculator and let me know what you get. People on YouTube, or they could plug it into. Wait again?
1,000. I'm sorry, 126,000.
126,000.
One person had a token or one person had a token. Well, again?
126,000 joules.
126,000.
Oh my. Well, yeah. Christopher, you tell me what you get.
I got 126,000.
Anybody get that?
Yes, sir.
Right. So
Yes, sir.
people on YouTube, let me follow you understand this first step. I had to find the energy that was actually transferred to the water, and only 35% was transferred to the water. People on YouTube, let me follow you catch my scene. YouTube people, talk to me fast. Are you understand why I find 35% of the total?
Yes, sir.
Yes, sir.
And I hear the YouTube people by YouTube people sticking by 104 people sticking by. Alright. So cool. So we know the energy that was used by the water, right? Is 126,000. So I know the energy here is
126,000.
126,000.
okay, cool. What was the mass of the water?
1.5 kg, sir.
Right, 1.5. They did tell us what the specific heat capacity was.
Yeah, it's for 4,200.
Kelani, I like your method a lot more, you know, right? Like I love it. I love it because in my method, when you had to make T2 the subject of the formula, it real long. Because you had to like expand brackets, move across things, divide. Kilani's a good boy. Big up Kilani one time. Double using the chat for Kilani, boy. Where's 1.5 by 4,200?
6,300, sir.
And if I want to find for the change in temperature, what do I do next?
Well, you had to make that the subject, so you had to divide by MC, so 1.5 by the 4,200.
Just divide by 6,300.
Yeah, on both sides.
So where you get? Where's 12600 divided by 6,300?
I get 20 degrees Celsius, sir.
Well, I get 20 degrees Celsius, guys.
Sir.
I'm not gonna put any units, right? Because we're talking about a change there. A change of 20. I'm not gonna put any units.
Oh, all right, yeah.
So here what? Here what, guys? What was the increase in temperature?
20, sir.
20.
Right. So here we're saying if the initial temperature T1 was 30 degrees Celsius, what do you think the final temperature is, chat?
50.
You had to add
Because
20,
the
so it would be
20 plus
50.
30.
Right.
Hey, physics is a real nice thing, you know, sir.
Now I saying physics real bad, physics real bad. Right? So people on YouTube, let me know if you understand why I found the change in temperature and then I added it to the initial temperature. Let me know people on YouTube. People on YouTube, let me know if you understand. It's a shame YouTube have like a little delay. Alright, cool. That was it for this the 6 mark question. Or the 6 marks. 6 marks.
6 marks, you know, sir. Wait, like 3 marks going there.
So where's 6 plus 1, sir?
7.
8.
Like that. 6 plus 1 is 7. Nikolai can't count to.
Nah, I can't count for one, sir.
Oh
Alright, so let me answer part 3, right?
Why you do maths?
Oh wait, Romano, you doing physics?
No, I just counted 5 while I do my IT.
Oh, okay.
Aren't you doing integrated science?
Yeah.
If you're doing that, this should benefit him, you know, this should benefit him. Because physics is like,
I do any electrical too.
okay, well, good. Yeah, tomorrow I'm gonna do electrical, alright? I feel a little more convinced to go a little past 10. I like the vibes, I like the vibes, I like the vibes.
Yes,
I like the vibes tonight. Yeah, boy. The vibes looking good. So why are the pipes made of copper? Why? Let me ask you a question, right? If water is flowing through these copper tubes, right? And your goal is to heat the water, why would you use copper tubes?
Because
Oh,
it's a
because
good insulator for heat. No, not insulator, but
conductor.
conductor.
Conductor. Number one. Copper is an excellent conductor.
So I was gonna say exquisite conductor of heat, you know.
Exquisite. Hey. I seen this too, Mark. So let me pull something else. Something else. Now, guys, since the copper is a good conductor of heat, good conductor. What? Remember your goal here? You have cool water passing through here. Remember that. So your objective is to get the heat absorbed from the sun to be transmitted to the what? To be transferred to the what?
The
Black
plates.
collector
To the
plate.
black collector plate.
Yeah, but like what flowing? Okay, you have
Oh,
water flowing through these copper tubes, you know.
Ah,
The
well,
heat, the heat is like being, the heat is gonna be transferred to the copper tube. But why we want that? What's our mission here?
to transfer
transfer
it
the heat
efficiently.
energy.
So
Right, we want to transfer the heat energy to the what? What we're passing through the pipes.
The tube.
water.
the water.
Exactly. Water is passing through the pipes. So since the copper is a good conductor of heat, it would transfer most of the heat to the water.
So isn't there a table with conductors and emitters?
Yeah, I'll share that just now.
Okay.
Okay, everybody understand this or not?
Yes, sir.
Yes, sir.
Right. And what's the name of this? These are solar what?
Solar water heater.
Solar water heater. Nice.
So when I look at this diagram, I always assume that, well, to be honest, I never read the question properly, so I would always assume that the heat was going into the copper tubes.
Yeah, like you have water passing through the copper tubes, and remember, like inside here gonna get real hot. Inside here gonna get real hot, and they're gonna heat up the copper tubes, and water passing through the copper tube, so the copper will transfer the heat to the water. So everybody, that makes sense.
Yes, sir.
Yes, sir.
You know,
It's like
since I
heat
start,
capacity as well.
well, yeah, I mean that's why we use it because you're changing the temperature. The
Oh, yeah.
water comes in. The water. Hey, hear what? Right? Hear what? Hear what? The water comes in at an initial temperature over here, but by the time it leaves, is a higher temperature. So for this whole process, we're using specific heat capacity formula. You know, E is equal to mc delta theta. So all the physics making sense?
Yes, sir.
Yes, sir.
All right, nice. Since I start these live learning, I never tell anybody I do lessons. Like I never tell anybody I do lessons, but yeah, guys, I do lessons. Like that just wasn't the main focus now. The main focus was just for it to learn how they work. Alright. So who wanna help me with this question?
If nobody willing, we will go.
You know how much people they have on YouTube and thing that want to be in these Zoom meetings, but because are they lucky, you know, like are they fortunate, like are they in here? Are they in the Zoom, you know what I mean?
Yes, sir.
So I want to
Or-
try.
yeah, read it on.
Okay. 4 factors of the surface of a material on which the absorption and emission of radiation depend are texture, rough or smooth, natural, dull or shiny, color, black or white,
Not natural.
sorry, nature, dull or shiny, color, black or white, area, large or small. State with a reason the appropriate characteristics of 2 of the above factors in design of a car radiator.
Alright. What do you want the car radiator to do?
Isn't that the the part where the engine is.
Right. So a car radiator, that's like the thing where you just like fill water in, you know what I mean? It's
Oh,
like,
okay.
let me just get an actual car radiator to show you. Just do that. Fellas, until you know a car radiator.
Yeah.
Ladies should know too. I feel like everybody should know is a car radiator. Ha. Looking for like a good image. So I'm gonna use these two images. Right? Alright, I don't know for the stream right now, everybody can see. Yeah. I see what I background.
Night.
Hi, good night.
She come to get some AC. Funny enough, we're doing thermal physics, you know what I mean? If you didn't know, I hope now you know. This is what a radiator does look like. Right? This is
So
what a
it's a
radiator
part
does
of
look like.
the car cooling system, right?
Is it part? Yeah, it's part of the car's cooling system.
Okay.
So let me ask you.
I didn't know how it looked, but now I know.
Now you know, right? Now you know. So let me ask you a question. I mean, you can see it for yourself. What color is this?
Black.
Black.
Black is
Black.
beautiful.
Right? Yeah, black is beautiful. And what color are the tubes?
Black.
Black.
Now, let me understand something. A lot of students have this misconception. And I like to tell me if I have it too. A lot of people think that black surfaces are poor emitters of heat. How much of you guys think black surfaces are poor emitters of heat?
No, that wrong.
That is wrong. That's very wrong.
I used to think about it
About
like that, but
lights,
now, sir,
no?
correct me. I understand it now. It is
So
not. It's not a poor emitter. It's a excellent emitter.
yeah. So let me run through the basics, right? So black is a good absorber of heat. Guys, if you have something black and it's a hot day and you're gonna feel the heat,
Yeah, I
Yes,
feel it.
sir.
Yes, sir. Black does
right?
absorb heat.
Exactly. And let me ask you a question. If something, okay, the hotter a surface of something is, does it emit more heat or does it emit less heat?
More.
More heat.
I hope you understand, all right? If something is hot, the hotter an object is, the more heat it is going to
Emit.
Emit.
Yes. So obviously, if something is black, it will absorb more heat, and therefore it will what more heat? It will what?
Emit more heat.
Emit more heat.
Yeah.
More heat.
Wait, but black surfaces are poor reflectors because they're not shiny. You
Yeah,
know,
they're not
they are
shiny.
poor reflectors.
Okay, sir.
So hopefully you understand that.
Yes,
Let me
sir.
look at white. White are great reflectors of heat. And let me ask you something. If it reflected most of the heat rays, would it absorb much?
No.
No, not
No.
really. It will do more
No.
reflecting than emitting or absorbing.
Right, so I want to let's think. Use our brain, right? So great reflectors. If they're great reflectors, they are not gonna absorb much heat. And if they're not gonna absorb much heat, are they gonna be cooler or hotter?
Cooler.
Cooler. And if they're cooler,
Will be
if they are
cooler.
cooler, right? If they are cooler, will they be good emitters or bad emitters?
So bad emitters.
Bad
Bad
emitters.
Exactly.
emitters. Poor
Because they're not
emitters.
gonna be hot. They're not gonna be hot, right? Man's not hot. Man's not hot. You know what I
Take off the
mean?
jacket.
Yeah, boy. They got big shack. So I hope let's see how these factors it's like a negative, it's like a feedback loop. Everything is connected. Dull. If something is dull, it's a bad reflector. If something is dull, it is a great absorber and a great emitter. And this makes sense. If it's a bad reflector, isn't it gonna absorb most of the heat?
Yes, sir.
Yes, sir.
And if it
Sir, I have
absorbs
an
plenty heat,
example for you.
some of us.
Um, Could we use a knife as an example? Because it have dull knives. It's
I
not a
wouldn't use
joke,
that.
it's just a serious thing.
I wouldn't use dull knife here.
Okay, okay.
But when she said dull, I thought it wasn't sharp enough.
Hey, that don't mean that kind of dull, right? I don't mean that kind of dull. Whoa. Hear what I'm saying, right? If you have like a matte surface, that kind of rough, that would be considered kind of dull. I mean, okay, dull is just the opposite as shiny earlier. So like, if you have like a matte surface, that's what I mean. So matte surfaces are dull surfaces and they are bad reflectors. Consequently, they are great absorbers and great emitters. Shiny. If something is shiny, it is a great reflector. And if it's a great reflector, it's not gonna absorb much heat. And that would make it a poor emitter as well because it's not gonna be that hot. Matte's not hot.
So we could use a mirror, for example, for that shiny.
Yes.
Okay.
Anybody know about the Dyson sphere?
Oh,
I heard it. I
Yeah, I
heard it
felt like I heard of
before.
it before.
If you know about CSEC, the
no.
YouTube channel,
No.
hey
Nah,
boy,
I
Actually,
don't
I'm too
really
young
watch
for that,
YouTube,
you
so now say
all,
that
all
that
the,
too. I too young.
listen, right? Hey, when I was in school, I watching Veritasium. I watching Three Blue One Brown number file. Um what's the other one?
Oh
Minute
yeah, I know
physics.
about that.
Minute
I
physics.
know.
I watching Kurzgesagt. Like I watching all these science things. Like I love science, Ollie. I love science. I love science. Ollie should try to explore science. Science real cool. But this is
So
effectively all.
I love physics. I love bio, and I'm starting to like chemistry.
That's good. That's good. You will love physics, eh? Chemistry cannot. I don't want to say anything bad about chemistry. Or mother will kill me because she's a chem teacher. But let's take a screenshot of this. Take a screenshot. Take a screenshot.
I took a picture already.
All right, cool. Let me answer the question. If it's a car radiator, we want to take the heat from the engine and do what with it?
Uh,
Emitter?
Yes, exactly. We want you to take the heat from the engine, take heat from engine, and dump it to the what?
outside, like
Yeah, dump it to the surroundings.
Yeah, basically.
So let me ask you a question. If I want to make a car radiator, will I use white or black?
Black, sir.
black.
I will use black. Why are you using black?
Because
Because
they
they're good
are
emitter
good
heat.
absorbers and good emitters.
Right, good absorbers and good emitters.
And should
And
we
end
use dull?
yes, it should be dull as well. It should be dull as well. Yeah.
But it have more than one options as to
You
we
c-
could choose.
you could choose a bunch. You could choose a bunch. So you
So
could say
I know they say texture, rough or smooth. You can put that in as well, or
yeah, you could put rough. You could put rough.
okay.
Basically, any characteristic that would help absorb is something you want. So I gonna say black and I gonna say dull. And Nikolai, we pick him dull because dull what? Dull what? What does dull do?
Is a core reflector. So it's a good absorber and emitter as well.
Good.
We basically already know the color that they're talking about is black.
For sure.
So
But a lot of people would make the mistake and they would put silver, but you don't understand, like, okay, you see how it's silver? Silver is not the main thing there, The fact of the matter is this is actually metal. And doesn't metal conduct a lot of heat?
Yes,
yeah.
sir.
Yes,
Yeah.
yes, it does.
Metal conducts a lot of heat, but that's not what we want. We're talking about these factors over here. So if we're talking about these factors strictly, then if we want to make a car radiator, the main thing we want it to do is take heat from the engine and dump it to the surroundings. So if it's taking heat from the engine, this particular part is going to be absorption. We want it to absorb heat. And then this part over here, dump it to the surroundings. I'm talking about what property?
Emit.
Emit heat, sir.
Emitted.
Earlier, physics don't have to be hard. Physics is plenty vibes, plenty vibes. Right? We okay with that? We get me 3 marks?
Yes, sir.
Yes.
We have
They said
math
two.
vibes and we have physics vibes.
Right. We have all the vibes. Yeah, this on YouTube. Just go on my YouTube channel. Make sure and subscribe. Math vibes. You know what I mean? Peak stuff there. Peak stuff there. And it said 2 characteristics, so that's fine. If you wanted, you could talk about area too. Which area would I use? Large or small?
Large.
Large?
No.
Correct me.
No, small.
Small.
Small surface area. If
Okay.
something has a small surface area, it would absorb heat a lot quicker. Anybody ever try to make a fire? Anybody ever try to make a fire here?
Yeah.
Okay.
One.
If you're trying to make a fire, right? Would you take like, okay, like when you have like a little fire, right? A little fire. Are you going to put like a big chunk of wood into the fire, or are you going to find like
Yeah, let's
like
find small pieces of sticks to make the fire. You can't.
exactly. So you need a small surface area. Well, I feel I said that wrong, boy. Let me just verify that. I feel like I said that wrong. Yeah, I feel like I said that wrong. Verify that. No, sorry. You want a higher surface area. Yeah. So like you see this like an inverse relationship. So like if you have a big block of wood, this actually has a small surface area. I know it really weird. It's like an inverse relationship. And if you have like a bunch of kindling, like a bunch of like a bunch of you have like a bunch of specks like grass or something, this would
Like
actually have
images.
high,
Images, sir.
yeah, this would have a high surface area. So if you want to absorb, if you want something to absorb heat, do you want a small surface area or a high surface area?
High.
A high
A
one.
high surface area. A high surface area. Because what would light faster? This or this? 1 or 2?
High. I mean two.
2. Yeah. Because I know
So
that was sounding real weird when I say it. I was like, that don't make sense what I'm saying. So I had to just verify it. Guys,
it's psychology,
if
sir.
if Alia, if Alia say something and it don't make sense, please check it. Please fact check it. Please fact check it. Yeah. So let's move on to the roof of a Caribbean home. Okay, when we talk about the roof of a Caribbean home, do we want to absorb heat?
Not emits.
Well,
Need
yeah,
shiny.
I mean,
Shiny.
you want to
It's already
absorb.
hot, so
It's
it doesn't-
shiny. Remember, it's galvanized we're talking about here.
Yeah, if you want to make a roof, right, you don't want it to absorb heat. You do not want it to absorb heat. You want it to reflect heat.
Right.
And so, what would I say? Would I use dull or shiny?
Shiny.
Shiny.
Because it reflects
Extra
more heat.
smooth.
It reflecting. It's a bad absorber, bad emitter, but
Right,
good reflector.
Yes.
reflects heat, bad absorber.
So the texture should be smooth as well.
Should be
Yes,
smooth.
Yeah.
So we bad like that. We bad
Smooth
like that.
criminal. Smooth criminal. It should be smooth
criminal.
because surfaces are good reflectors. Good reflectors.
One question, sir. Should we use the area as a large, which have the small surface area?
Okay, let me just verify that. I don't want to tell you anything wrong. I really don't want to tell you anything wrong. I wouldn't tell you to use that one day, boy. I wouldn't tell you to use that one day.
No, because like you know when you buy galvanized, it'd be big pieces. So just put it together.
Yes, sir, I was gonna tell you that. When you buy it, it don't really be no small things, be big pieces.
Yeah.
Depends on the size of your house.
No, but even if you have a small house, you still have big pieces.
Yeah. Because it has to cover everything. You don't want to
It
rain to
would,
fall
it,
on inside your
I would
house.
say large area. I would say large area, but when we're talking about surface area, it kind of inversely proportional. It's kind of inverse. So if something is really, really large, it would have a smaller surface area. Like I know it's really, really weird. It's like really, really weird. It's like really, really weird. Like I'll do some research on it, right? Like just look up. If something is large, would it have a small or large surface area?
Well, people who don't know this would say the large would have a large surface area.
Exactly. So, like, okay, if you look it up, you'll see that large objects have a larger absolute surface area, but a smaller surface area in proportion to their volume.
Huh?
Yeah, it's a bit confusing. So, here what I'm saying, right? If something is really large, it's gonna have a very large volume, and its surface area is going to be much less than the volume. So the ratio there is going to be less. So
So
I wouldn't advise it to use area. Stay away from area. It might be a bit confusing, that one.
yeah,
Yeah.
but seeing that we was exploring, it was kind of curious as to what area you would have used. So
Well,
if it was a large piece but a small surface area, would that reflect or would that absorb?
okay. If it is like really, really large, okay, if its size is large, then it would have a small surface area later because the volume would be a lot more. I can't give you a specific answer on that one, right?
Uh,
Like I thinking about it, and for the roof of a house, nah. But generally speaking, the absolute area is large. The absolute area is large. But if we're talking about surface area, with the ratio of volume to surface area, it kind of different. So I would stay away from that one. The
yes, sir.
easiest one to use here is shiny and smooth. Good
Yes, sir.
reflectors.
I feel CSEC put out there for we to get confused.
Nah, like if you know area, you could put it, but I would stay away from that. Like the safest ones are color and nature and texture. Safest ones.
Also,
And seeing that the area
leave
have
on
a
area.
reverse psychology of it.
Okay.
Yeah. And I would use white. I would use white as well. White would be a good one. They only said two, so you could pick any one out of these three.
White. Good
Because
reflector.
white,
So I believe when I was doing physics before and I wasn't good at physics, I believe I put in the area for some reason.
I will I will try
I
to
feel
tell you a good
like
answer in terms of area. Like
I feel
actually,
like
like let me look it up. Let me look it up right now. Because surface area is kind of it isn't as straightforward as you think.
I don't
The
like for
math
the plant. I don't like for the plant when they have a small thing and have a large surface area, meaning that when the sun hits the leaf of the plant, it diffuses into the insides of the plant, like the epidermis, the sponge in there, and all this sort of stuff. But seeing that is galvanized, and we already know that the galvanized is shiny, the large surface area, I would believe would more reflect.
okay, so like if we're talking about area, I don't think CXC talking about surface area, you know. I think they're just talking about absolute area. And well, if it's a car radiator, you'd want a large area. Why a large area? Because you'd want it to, like, okay, think of a heat sink, right? If I want to transfer as much heat as possible, would I want a large heat sink or a small heat sink?
Large?
A large
Large.
heat sink. You see this you see like this aluminum here, like this big aluminum thing with like ridges.
Yes, sir.
That's called a heat sink, and it's like large. So I would say like if we're talking about area, I just now research it. I would say large area. Large area over here and large area over here. I was overcomplicating it with surface area.
Ah,
They just ask area, so large area. But I would not, I would not put the area.
it's
I would not
because
put the
you
area.
lose max. So you can lose max for that.
Yeah, just stick with the safe ones, guys. Stick with the safe ones. Stick with the safe ones. So let me know if you guys understand black, white, dull, shiny.
Yes, sir.
Yes, sir.
Yes,
Okay,
sir.
so that's an easy 6 marks, right? Easy 6 marks.
6
And
marks. Tag.
if you guys want, you can take a screenshot of this.
Yes, sir.
The match. I'm curious why for a roof would I want? Because like a lot of these things, you want to say the most obvious answer, but like sometimes it's be counterintuitive. Right, right. So yeah. It's very counterintuitive, right? So here's what ChatGPT said. For a roof, the answer depends on whether your goal is to gain heat or reduce heat transfer. But in most real-world situations, you generally want a smaller exposed area if all other factors are equal. And that kind of makes sense. If you want the roof, okay, the bigger the roof is, right? If the roof is huge, we know it's shiny and thing, right? So it would absorb most of the heat, but the bigger the roof is, would you okay, if the roof is huge, do you think it's gonna absorb more heat or like okay,
Absorb
compare
heat.
compare a huge roof to a small roof. Which one would absorb more heat, generally speaking?
The small one.
The small
Think of
ones.
it like the same sticks and the plank wood.
Exactly. So if you want to make the most ideal roof, you want to use the least material possible. So you want to like minimize the amount of material you're using for the roof. If you understand what I mean. Because the bigger the material, like the bigger the surface, it would allow like okay, more sun rays are going to hit it. If you understand what I mean. More sun rays are going to hit it. Alright.
Okay.
So
Just avoid the area. Just avoid the area.
yeah, just avoid that. Alright, so who wanna help me with this question?
I think this is with the heater, the kettle that I was talking about.
Right, so well, Nikolai, we could run it. Renisha, I see I have your hand up.
It was for the previous question. So they say small surface area, less exposure, less heat transfer, and the large one is more exposure, more heat transfer. Don't know if that correct.
That's correct. That's correct. But I feel like I just with the area. Right? Okay. Part B. So Nikolai, get a read from her.
The following data were obtained in an experiment using an immersion heater to determine the specific latent heat of vaporization of water. Do I have to read this thing? Like the mass of can
Yeah, read
and
it. So actually I'll read it fast. So the mass of can and water at the start of boiling, M1 is 0.28 kg. And the mass of the can and water at the end of boiling, you notice that the mass is more or less.
more.
Well, this is after, yeah. This is after.
You talking about the one on top? That is more than the one underneath?
Wait, I'm talking about after. After it got
Oh,
boiled. After it was boiled. Onto the
less.
mass.
Is less.
Less. Good. So, Ollie, talk to me logically, right? If you put you're dealing with an immersion heater here, so like you're heating up the water. So if I'm heating up the water and I notice that the mass drops, I mean some of the water would have been converted to what?
Gas or air.
Steam.
Or
Steam.
steam.
Not air. Not air. Steam. Steam.
Yeah, my bad. My bad.
Now the power of the heater is 150 watts and the time of heating is 5 minutes. So using the data above, calculate the specific latent heat of vaporization of water. So let's recall this formula immediately. What's the formula for specific latent heat of vaporization?
E is equals to MLV. Or small v.
Are you understand that or no?
Yes, sir.
Yes, sir.
So, Nikolai, like I said, if you are boiling water and you notice that the mass is lesser, then what would happen to some of the water then?
It will be converted into steam.
Exactly, and that's why your mass is less. So, Nikolai, would it be possible for me to find the mass of water that was converted to steam?
Yes, sir.
Okay, how could I find the mass of water converted to steam?
By minusing the initial mass by the final mass.
So that would be 0.28 minus what?
0.26, which is just 0.02.
So everybody, people on YouTube and thing, if you boil water, isn't the mass after going to be less? Because some of it would have been converted to steam and it would have been transferred to the atmosphere.
Yes, sir.
Yes, sir.
People in the Zoom, are you understand that or no?
Yes, sir.
Yeah.
Yes, sir.
All right, so you understand how I find the mass of water converted to steam on that?
Yes, sir.
Yeah.
Okay, cool. So I have M. If I'm trying to, they want me to find LV. That's what they want me to find. Now, if I'm trying to solve an equation, I need one unknown. So what else do I need to find?
E, which is the energy.
Energy. Good. Now, Nikolai, notice they give us the power, and what else did they give us?
Time.
Is there a formula you could think of that has power, time, and energy in it?
Yes, sir. P is equal to energy over time.
Okay, do you guys know that power is equal to energy over time?
Yes, sir.
Yes, sir.
Okay, good. That reminds me, what is the SI unit for time in physics?
Seconds.
Seconds.
Second.
So, like, could I work with 5 minutes?
No, you'll have to convert that into seconds.
156, sir.
So I gotta multiply by what, Nikolai?
60, because 60 seconds is 1 minute.
So where's 5 by 60?
That would be 300.
Cool, 300 seconds. So here what? If I know power is equal to energy over time, is it possible for me to find for energy, granted I know what power and time is?
Yes, sir. You make E the subject of the formula.
That's correct. So I know my power is 150. I don't know what my energy is, but I know that my time was 300 seconds. So what should I do here, Nikolai?
Oh, yes, you multiply by 300 to cancel off the 300 at the denominator. So you'll be left with E, and you'll have to multiply the 300 on the other side as well. So it'll be 150 multiplied by 300, which is 45,000.
And what's the units for this? So it's energy.
Joules.
Right, people on YouTube, let me know if you understood how I found for energy using the power and the time. People on YouTube, let me know if you guys understand how I found for energy using using the power formula. So okay, we have the mass of water converted to steam, and we have the energy. So tick and tick. So let me plug that in now. So where's the energy? Come on, Nikolai, where's the energy?
Energy would be the 45,000, but wouldn't we convert that to like 10 to the power minus something? Or is
No,
that
no, no, no,
necessary?
no, no, no. It's already in joules. It's already in joules, so we could work with it.
Okay.
In the last question, it was kilojoules. He had to convert the kilo to 10 to the power 3.
Okay.
So long story short, Nikolai, if you see something other than joules, you have to multiply by the prefix. So if I saw megajoules, I would have to multiply by 10 to the power 6. But seeing that it's just joules, we could work with this one time. So 45,000 is equal to the mass. What's the mass?
The mass is 0.02.
So I gotta divide both sides by what?
0.02. So you'll be left with LV on one side, and when you divide the 45,000 divided by 0.02, I got 2,250,000.
2 million.
250,000. Yes, sir.
And what would the units for this be? And Nikolai, let me share an easy way to understand this, right? Say with my Nikolai.
Yes, sir.
If you wanted to find for LV, it had to divide both sides by what?
By the mass, which is kg.
So you end up with energy over mass. Energy is measured in what?
Joules.
Mass is measured in what?
Kilograms.
So your units would be joules per kg.
Okay. Wouldn't? Okay.
Because
Did
what
you
do we
say
measure mass in? What do we measure mass in?
kilograms?
Exactly, kilograms. Did you guys understand how I derived the units if I forgot it?
Yes, sir.
So,
Yep.
Good. Because you understand is energy over mass. Energy is joules, and if I divide by m, it will be over kg. So joules per kg. Simple. People on YouTube, people, Kelani, anybody on Zoom, did you guys get through with it?
Yes, sir.
yes, sir.
No problems.
Okay, good. People on YouTube, let me know if I get through. People on YouTube, did you guys get through? Can I hear from the people on YouTube? It have 101 people on YouTube, guys. That's crazy. Wow.
Physics is vibes, you know, sir.
Yeah, boy, physics is vibes. Right, so our Kelani self know this question. So Kelani, give it a read.
All right, so the coil of the immersion heater was not completely submerged. Explain how this would have affected the value for the specific latent heat of vaporization on page 17, right? So
First of all, do you know what an immersion heater looks like?
immersion heater, not familiar, but I know what a heater gives off heat, so that is just what I'm
Hey,
going by.
you guys use it all the time. You have hot water in your house?
Yeah, it's like a kettle or something.
Well, yeah, it have immersion heater kettles.
Right.
I'm trying to find a good example for you though, where you could see it exactly. Yeah, I guess I could use this one. Suppose. Like a lot of the times you guys read things on paper, but you don't understand what the heck it even looks like. So
Yeah.
how are you going to make sense of it if you don't even know what it look like? How much y'all have like well, hot water in all your showers?
Yeah.
Me,
Me.
sir. Well, I believe
So
everybody have that.
And
you mean the kind of shower that let's put the switch outside the bathroom, then you can turn it on and your water will be hot? Or you're
yeah,
talking about
yeah.
kettle?
Both use immersion heating. Both use immersion heating.
Oh well, yes, I'm aware of it.
So I can't teach you some physics, boy. Because I sure you learn about these things. Right, so watch this. So let me show you something, right? So Kelani, it's gonna
Yes,
make so
sir.
much sense for you. It's gonna make so much sense for you. Here what happening, right? You have one of these one?
Yeah.
Okay, let me explain how this is work. So the water would flow inside this chamber over here, right?
Yeah.
When the pressure gets high, it lifts up a plate which makes contact with a coil. And the current runs through the coil and the coil gets hot. And the water in this chamber gets heated by the coil. Because you'd imagine, Kelani, if the coil gets really hot and the water is in contact with the coil, what happens to the temperature of the water?
It would gain heat.
Exactly, and the water that falls out is going to be what?
Well, the result of the water getting heat. So your body would feel the contact of the hot water.
Exactly, you feel the hot water. So this is what
Yeah.
it actually looks like on the inside. Can you see the coil?
Yeah, I've seen it, yeah.
And so you would make a live connection here. You'd hook this up to your wall. And so what happens is, water would be in this chamber and this coil would heat up. You understand? This coil would heat up.
Right.
So the water is going to rush in through here and it's going to populate this chamber.
Yeah.
And so the water, okay, and so the coil is immersed in,
The water, sir.
yeah, and when the pressure is enough, it causes the coil, it causes the coil to come on and current would flow through the coil, causing it to what?
Heat up.
Right. And since the coil is immersed in the water, what's going to happen to the temperature of the water?
The water will get hot.
Exactly. Exactly. Now, if it was not fully immersed, would I need more energy to heat the water or less energy to heat the water?
Well, if it wasn't fully, you would need more energy.
Exactly. Exactly. So let me cook, right? And if I using more energy, would that increase my specific latent heat of vaporization or decrease it?
Nah, it will raise it. It will raise it.
Exactly. You go raise it. You go
Increase.
raise it. Yeah. So people on YouTube, if you didn't know now, you know. This is an example of an immersion heater. I'm sure somebody didn't know that. And
Also,
well,
now, oh, well, yeah, now I could kind of formulate the answer for the question, you know, now that I have an understanding.
So this is a cool experiment. I now knowing this thing.
well, like your kettle too, right? Your kettle, it have a coil in the kettle, right? To the bottom, and it's hooked this up to the
The cord
socket.
extension cord. Well, not the extension cord, but the cord basically.
Right. So when you put on the switch, current flows through the coil, and you see this metal plate over here. What would happen to
Yeah.
it?
It heats
It will
up.
gain heat, yeah.
It would gain heat. And what is immersed?
The
Okay, is it
water.
exactly? Isn't the water in contact with this metal plate?
Yes.
Yes.
So
Wait, hey, we using it, hey, we doing this every day, you know, sir.
yeah, but you just don't make the connection.
Wait.
And so the metal plate is immersed in
In the water.
Water.
exactly. Yeah, and like so many kettles, if you look, you'd actually see the coil exposed to the side. I don't know if I'll ever see that.
Wouldn't that be
Like,
kind of
probably.
contaminated or kind of bad?
Well, they just use something that's not very reactive. Chemistry people, until they should know about the reactivity series.
Yes.
Oh,
Sir,
yes.
hey, sir, I made sure and remember that whole thing. And that thing did not come in the exam. I was
Hey,
like, hey boy.
No, actually, one of the questions you had to apply the low reactivity series.
well, Nikolai. Ooh. Well, let me not worry about chemistry and worry about physics, right? So guys,
Oh, wait,
Kelani,
what?
so Kelani,
Yes,
let me
sir.
just say the coil was over here, right? And I fill up
Yeah.
the water line to the over here. Is the water fully immersing the coil?
No, not fully. That's partially.
And so will all the energy be transferred to the water?
Nah, that means okay, so if it partially submerged, you would have to use more energy
More energy for the for
for
the
the
equivalent effect.
right, yeah.
Right. So you see, it makes real sense. So talk to me. If the coil of the immersion heater was not completely submerged, how would that affect the value?
If it is not fully submerged, then the value it wouldn't be where it need to be. So you need to apply more heat to raise the value. Um, you need to apply more heat to raise the value. Since uh what to say, boy, is like they're asking how they say to explain how this would affect the value. How this would affect the value. Could have
Okay, here what Kelani. Let me write down the formula, right? Let me write down the formula. So we know the formula is E is equal to MLV, right?
MLV, yeah.
If you make LV the subject of the formula, it will be what over what?
That'll be E over M.
The E over M, right? Now, if the coil is not fully submerged,
Submerged, yeah.
some energy will be what?
Some energy would not be in contact with the would not be in contact with the water. No?
So some of the energy will be wasted, right? Because you have some of the
Yeah.
energy being lost to the environment. So if the
Yeah,
coil is
wasted.
not fully submerged, some energy will be wasted. Wasted.
Wasted, yes.
Therefore, more energy
Would be required
exactly will be required.
to increase the value.
Will be required to. I wouldn't say that in the context of this. I would say will be required to change the water to steam. Right, so if the coil is not fully submerged, more energy will be wasted. Therefore, more energy will be required to change the water to steam.
Yeah, that's a perfect. Yeah, that makes sense.
Since energy is increasing, LV will also
Increase
increase. Why?
because it's directly
As
proportional.
exactly as per LV is equal to E over M. Guys, if you're confused, if the value on top is bigger, what happens to the total answer?
We get bigger as well.
Exactly. Here what? I want you to compare 10 over 2 to 100 over 2. Which answer is bigger? 1 or 2?
2.
2.
2. So I hope you understand. If I'm using more energy, what happens to LV?
It will be
Increase.
increased.
It will increase, right? Obviously, there's more eloquent ways you could state your answer, but I'm not an English teacher. But I had the general concept here. If the coil is not fully submerged, some energy will be wasted. Therefore, more energy will be required to change the water to steam. Since energy is increasing, LV will also increase as per LV is equal to E over M.
Yeah, I like that answer. So it actually making sense.
Right? It makes sense because again, if it's partially submerged, you see all this heat over here,
Yeah.
it's gonna be wasted. It's gonna be wasted. And so now you'll have to leave the kettle on for a longer period of time. And if you're leaving it on for a longer period of time, more energy is being used. It makes perfect sense.
Yeah, that's why on the kettle it have it have different temperatures. You could hot the water.
Well, I was gonna say that is why it have like a recommended fill line. You have like a
Oh,
recommended line.
yeah,
Yeah.
that too.
Okay. So I hope all you're seeing how practical physics is. Right? Who wants to help me with the cooling on cooling curve? Is it heating on the cooling curve? Who wants to help me with this question?
There's an next part to it. Let's just go one time.
Right.
Okay.
Somebody said, "Sir, we have to say the same amount of water in the same amount of time." Yeah, you could say that as well. You would need more energy to convert the same amount of water to steam. All right, so a substance which has a melting point of 80 degrees Celsius is cooled from 90 degrees Celsius to a complete solid at its melting point. Sketch a graph in figure 1 to represent this statement above. So, Nikolai, what temperature are we starting at?
We start at we start at 80.
No,
90.
read that read it back to
Oh,
my
the
Nikolai.
substance
Again.
which is a substance which has a melting point of 80 is cooled off from 90.
Hey, I feel like all I should have enough trauma from bearings, from bearings.
Yeah, boy.
Yes,
Yeah.
sir.
Anytime I see the word from, that's where it's starting from, you know what I mean?
Yes,
So
sir.
This 80 degrees Celsius is really a melting point. Melting point. But you're starting from 90 degrees Celsius. So Nikolai, I got a parallel 90 degrees Celsius here, and this is where I'm starting from, you understand?
Yes, sir.
Right. And is the temperature increasing or decreasing? They said it was a cooling curve, so what do you think?
It decrease.
It decrease. And obviously if it decreasing, would I put a negative slope or a positive slope?
Negative.
Right, and a negative slope does look like this. What trying to do, we're trying to tie in the odd maths, the maths, and everything you learn. So they go understand its use cases. Right? So this makes sense because it's a negative slope. I mean, if it's a negative slope, the value decreasing. Right? So cool. So Nikolai, we're cooling it from 90 degrees. And Nikolai, what is the melting point of this thing?
It was at 80.
So when I cool it to 80 degrees Celsius, what will happen?
It remains stagnant, like it's a straight line.
It's a straight line. And why is that? Let me explain. Enter the melting point. Okay, at the melting point, as a solid would be something would be converted from solid to what?
Liquid.
Or vice versa. Now, if you're experiencing a change in state, then we're talking about what type of we're talking about over here.
Solid to liquid.
There's
Phase change.
Specific latent heat or what?
fusion.
Oh, fusion.
And when this happens, what we know about the temperature?
It doesn't be affected. It's not affected by temperature.
No change in temperature. Well, you understand that?
Yeah.
Yes, sir.
So
Yes.
connect all the dots. For this over here, the gradient is 0, which means it's not changing. So can you guys see when it reaches its melting point, there's going to be some time where the temperature remains Z?
Same.
Same.
Or constant. Could you say constant?
Yeah, you could say constant. And this would represent the specific latent heat of fusion part. Hope you understand that.
Yeah.
So Nikolai, what would you describe the state as over here? Above
If
9,
it is
above
if it
80, above 80 it will be a what?
a liquid.
Above 80 it will be a liquid, right? And in this period over, this is a transition period. So Nikolai, in this period over here, it's going from liquid to what?
Solid.
And then you're cooling it again. So over here it would now be a what over here?
A solid.
Did my Apple Pencil die already? No, it didn't die. Why people in trouble? What? Come on a second.
Trying to tamper with the physics 5, sir.
What's going on there? Oh, never mind. It was just on white. Oof. Yeah, so Nikolai, it'll be solid over here. Let me know if you guys understand cooling curves.
Yes, sir. Chemistry,
So,
right?
so again, guys, we started off at what temperature?
We started off
90.
at 90.
90 degrees Celsius, and we're cooling. So will the temperature increase or decrease?
Decrease.
Decrease.
Right. It decreasing. When we reach the melting point is the transition point where it's going to go from a liquid to a what?
Solid.
Solid.
But at that transition point, there's going to be no change in temperature for a little while. So I represent that as a horizontal line. And once the atomic structure is fully rearranged to a solid, it's gonna be we're gonna start the temperature is gonna start changing again. And so this period over here would be when it's a complete solid. And this over here is a complete liquid. And this over here is the transition period when it's going from a liquid to a solid.
So change in phase.
Correct. And here what? Nikolai, do you think you have what it takes to draw the heating curve for this?
Yes, sir. It will just be like the opposite direction of the cooling curve.
Well, let me see. After tonight, I want to let you think about physics differently. I'm not here to just I'm not just here for it to memorize. I'm here so all you will develop a deeper intuition for these things. It's not just about writing on a piece of paper, it's about understanding physics. Right? These are
Confidence in doing the physics.
yep. So if it's a heating curve, what are we doing with the temperature?
Rising.
We are increasing temperature. So here what? What if I told you we started from 0 degrees Celsius. So let's start from 0 degrees Celsius and I want you to heat it. All right, so Nikolai, and I'm telling you that has a I'm gonna change it up. How I melt it? Actually, I will stick with the 80 degrees Celsius to keep it consistent. So Nikolai, let's look at the heating curve. So you know for a heating curve, you're increasing the temperature with respect to time. So we starting off from 0, right, Nikolai?
Yes, sir.
So we have temperature here, and we have time on the time over there. All right, so Nikolai, what to do?
Well, it'll go up in a positive gradient.
And I should go up to what temperature?
80.
I should go up to 80. Now tell me, Nikolai, from 0 to over here, what is it?
It's a solid.
And over here, am I just gonna keep increasing or what's gonna happen?
No, so you'll have a change in phase.
Right. And over here, it's going from solid to what?
Liquid.
And once it's fully a liquid, it's gonna start to increase temperature again until it reaches what temperature? What do we stop at?
120 degrees.
Guys, do you all understand cooling curves and heating curves now?
Yes, sir.
Let me know if you guys understand anything.
Yes, sir.
Are they sure?
Yes.
Very sure.
Very sure.
Yes, sir.
Okay, and if I told you at 120 degrees Celsius, it is the boiling point. Alright, that's the boiling point. And I continue to heat it. What happened over here?
It'll be at a change in phase from liquid to gas.
The line will be flat.
Right, and over here go be liquid. And over here go be liquid to what? And we transitioning from liquid to what?
Gas.
Gas.
And over here will be a gas. Good job, guys. Good job. Good for yourself, man. Yeah. So here what? After we've done everything tonight, we will look at the question in the 2025 paper. Right? But after today, we should be okay with thermal physics. Should be okay with it. Alright. So Alicia, are you okay with this?
Yes, sir.
Okay.
So,
Who want to help me with this question?
There we go.
sure, there we go. Oh, wait, who says so?
Kilani. I hear what? I will let Virginia help me with this. Yeah.
Okay.
Because I see Virginia on mute. She wanted to give it a go. Right, so Virginia, a
Yes.
physicist converted 2 kilograms of water, at 37 degrees Celsius to what?
100 degrees Celsius.
To steam at 100 degrees Celsius.
Oh, yeah.
So before I even do anything, I'm going to do like a flow of the process. So we're
Okay.
gonna start off with water at what temperature?
37 degrees.
Wait, tell him ask Nikolai something. Nikolai, do you think that this will be how the process looks like?
Nah. It'll be
Nah,
the same.
so Virginia, corrected. Tell me what happened, Virginia.
Well, first you would have to boil the water to 100 degrees Celsius.
So we have water here at 100 degrees Celsius. And what
Yeah.
next?
Then they'll have the state change to steam, which will also be 100 degrees Celsius.
People on YouTube, let me know if you understand this. People on YouTube, let me know if you guys understand this. So we have to go from water at 37 degrees Celsius to water at 100 degrees Celsius and then to steam. Let me know if you guys understand that. People on YouTube, let me know. It doesn't just go straight from water to steam. You have to heat up the water to 100 and then it becomes with the steam. See, somebody said no, sir. Okay, so Peter, here what happening, right? For different states of matter, the atomic structure is different. And so if it's a liquid, the atomic structure is going to be different from when it's a gas. And so what we have to do is we have to heat up the water to 100 degrees Celsius first. And when it's 100 degrees Celsius, we need that extra energy to change the atomic structure to a gas. And that extra energy there is called latent heat of vaporization. So you see, Peter, we heat up the water to 100 degrees Celsius, but it isn't steamers yet. It is not steamers yet. What we have to do is we have to rearrange the atomic structure to turn it into steam. And that extra process there demands some energy. And during this process, there's no change in temperature. So guys, water at 37 to water at 100 and then steam to 100. Cool. Okay, if you're still confused, guys, I'm going to explain something. When you're boiling water, and you would see, okay, if you feel the water, right? Okay, like if you're seeing steam from the pot, if you feel the water, wouldn't the water be very hot?
Yes, sir.
Yes, sir.
Okay, so people on YouTube, if you're boiling water, people on YouTube, right? Think about this, and people on Zoom. When you're boiling water, doesn't the water have to get really hot first?
Yes, sir.
People on YouTube, let me know if you understand what I'm saying. When you are boiling water and you're converting the water to steam, doesn't the water have to get very hot first? So I hope that makes intuitive sense. When you're boiling water, the water has to get really hot first. So the water would be at 100 degrees Celsius. But then you need some extra energy to rearrange the atomic structure for it to turn to steam. So that extra energy happens with no change in temperature. So first you had to heat the water to 100 degrees Celsius, and then you need to give it that extra push to become with the steam, but the temperature will be the same. If you measure the temperature of boiling water, it'll be 100 degrees Celsius. If you measure the temperature of steam, it's also going to be 100 degrees Celsius. So I hope you understand that. When you're boiling water and you're converting it to steam, you have to heat up the water to 100 first. And then when you give it the extra energy again, it'll become with the steam at that same temperature. So you need that extra energy to just change the atomic structure, to make the phase change. All right, so Virginia, tell me what to do next.
So for the first part, there's a change in temperature, so use the formula MC delta theta.
Right, and for the next one, we're going to use which formula?
So because there's a change in states, we'll use MLV.
And we'll use vaporization because we're going from water to steam. We're vaporizing the water. That makes sense.
Yes, sir.
People in the Zoom, are you with me so far or no?
Yeah.
Yes, sir.
Yeah,
I
good.
just hear quiet listening and observing.
No problem. Assuming no heat is lost, calculate the amount of energy needed to heat the water to 100 degrees Celsius. So Virginia, if we heat any water, is that a phase change or just change in temperature?
That's a change in temperature.
Right, so we'll say E is equal to MC delta theta.
Yes, sir.
What is the mass of water we're heating?
2 kilograms.
that was said in the question. Nice.
Yes,
What is
sir.
the specific heat capacity of water?
I think it's 4,200.
Yeah, 4,200.
Okay, nice.
And if we started off at 37 degrees Celsius and we reach 100, then what would I do to find a change?
Subtract 37 from 100, which will be 63, if I'm not mistaken, right?
Yeah, that's correct. So it'll be 2 by 4,200 by 63.
Okay. And
So
I got 529,200 joules.
wait a So like my brain tweaking. So 529
Wait,
529,000. That's what you get, right?
and 200. So, like, change the first 0 to 2.
Or
Yeah.
59 or 529,200.
Yes, sir.
That's what you get? Okay.
Yeah.
Anybody else got this?
Yes, sir.
Right.
Yes, sir.
Okay, good. People on YouTube, let me know if you guys got this. The 529,200 joules. Yep. Anybody on YouTube, did you all get this? After I finish all these lives and thing, I gotta rock back and relax for a good couple, like a little while actually. People on YouTube, let me know if all they get through. Yeah, okay, good. Right, now we wanna calculate the amount of energy to heat the water from 100 degrees Celsius to steam at 100 degrees Celsius. So which formula are we gonna use here?
MLV.
So again, what's the mass of water we're trying to convert?
2 kilograms.
So that's gonna be 2. And the latent heat, the specific latent heat of vaporization is 2.3. That is 2.3 by 10 to the power 6.
Okay.
So that should just be 4.6 by 10 to the power 6.
Yes, sir.
Now, if you wanted, you could instead of saying 10 to the power 6, we could say instead, what's the prefix for that?
Megajoules. So we could convert it to megajoules.
Yeah, if you wanted, you could have said 4.6 megajoules. If you wanted.
Well, that's
Earlier,
what my teacher usually does when it's a large number.
yeah, you could apply the prefixes. Guys, let me know if you all are with me so far. Does it make sense?
Yes,
Yeah.
sir.
Oh yeah, that's 7 marks. You just get there, 7.
That's
Listen,
Serious?
7. That's 7 marks. You just and the other 9 marks. You just don't get 9 marks. That's
wow.
great. Physics easy, genuinely. Right? And well, the last part, to completely convert the water from 37 degrees Celsius to steam at 100 degrees Celsius. So how are we going to do that, Virginia?
Well, I guess we just add the two
That's all.
amounts of energy.
So to find the total energy, that's just going to be the 529,200 plus the 4.6 by 10 to the power 6.
Okay, so I got 5,129,200 joules.
That's what you got, right?
Oh, yes, sir. I just realized it on the screen.
Yeah, let me know if you're okay with this.
Yes, sir.
Yes, sir.
Yeah.
Badness. Hey, how the finance class going so far, boy? Easy or hard?
Easy.
True, we getting
Easy
through.
so far, sir.
Easy,
So, like, we
boy.
go to 11 now, sir.
Say that again?
Like, we go to 11 o'clock now, sir.
That's not a problem. I feel any vibes in it. Right. So here what? Now we need to look at this particular thing for thermal physics, which is the part that already like kind of boring. We need to compare the three types of thermometers. So, and the three types of thermometers are liquid and glass, clinical, and thermocouple. So, if they ask you for the physical properties, these what you need to know. So, for liquid and glass, the physical property is expansion of mercury. So, we're looking at what there? If it's expansion of mercury, talking about what? That's what V. Something expanding.
The volume?
Volume.
And well, clinical expansion of mercury.
Is the
Sometimes it is use alcohol too, eh? But you should also note this as well. Mercury is preferred to alcohol because it has a much higher boiling point, 357 degrees, whereas alcohol is 78 degrees Celsius. It's typically why we use mercury, because it has a higher boiling point. Right. So for liquid and glass is the expansion of mercury, that's the response factor. So that's volume. Clinical, that's expansion of mercury volume. For thermocouple, it's voltage. So if you have two different types of conductors and you apply, okay, you'll have a hot junction and a cold junction. Between these two, you'll get a potential difference which will generate a voltage. Yeah. So let me show you guys what a thermocouple looks like. Because I presume you know what the other types of thermometers look like, yeah?
Yes, sir.
Yeah.
Right, this is what a thermocouple looks like. Yeah. So to use a thermocouple typically has two different types of wire that's connected to a cold junction. Obviously, that would be colder than the hot junction. The hot junction is in contact with a hot object. And this would go to a multimeter or a voltmeter. And you would see, you get like a reading in millivolts, and that would be calibrated to a specific temperature. Yeah. So like there's a table that tells you what the corresponding temperature is for the millivolt reading. Hope that makes sense. So I'll like to take a screenshot of this. So for liquid and glass, the structural adaptation is a long stem for wide range of readings. For clinical, you have a large thin bulb that conducts heat quickly. Obviously, if you're working in the clinic, you don't want to wait an hour for to get somebody temperature. You want to be able to read that quickly. So it makes sense why we're using a large thin bulb.
Yeah.
It has a small range of temperatures, obviously, because humans are typically around 35 to 45 degrees Celsius. You have okay, let me show you what clinical thermometer does look like so you could see what I'm talking about better. Where's like a good one? Can't find like a good image. I'll prove my point. I find it. Check this out, guys. Where did they go? And when the nurse tells you to put the thermometer in your mouth, they would like typically leave or something, and then they would come back, and then they would like take it out of their mouth or something, and they would take the reading.
Yes, sir.
Do you want the reading to change as soon as they take it out of your mouth?
No.
No. Oh.
No. So that's why I have a constriction, right? So we just did the kinetic theory of matter. So when you apply heat to the bulb over here, filled with mercury or alcohol, you are applying heat to the substance. And when you apply heat to a substance, it would gain kinetic energy, and it would push against it would push against the walls, and what would happen to the volume of the substance?
It would increase.
It would increase, sir.
Exactly. And if the volume is increasing, it's going to occupy more space in the thermometer, so it's going to rise. Now, the constriction is here, so it prevents the liquid from flowing back easily to the bulb.
Yeah.
So I hope that makes sense.
It's like a resistance.
Yeah. We might end like 11 or 12 or so. So I hope all you understand the structural adaptation that goes on with a clinical. So at least if you forget in the exam, you cannot understand the intuition behind it. And well, a thermocouple has the widest range of temperature. It's really useful. We just typically don't use it because when do we want to measure something that's minus 200 degrees Celsius? You know what I mean? When do we want to measure something that's 1250 degrees Celsius? Do you find yourself on a day-to-day basis trying to measure something this cold
No.
Nope.
or this hot?
No.
Nah.
Well, if I wanted to measure the hotness of Mrs. Matt vibes, I would probably need this.
Hey.
Sir, you probably need more than just one, sir. You probably just need more than one.
Probably need more than one. Yeah. I thought the physics reason or the physics reason. Ah. Right, quick accurate readings can measure from junctions of small masses. So take a screenshot. Or they can take a screenshot of this. Yeah, I don't remember this.
You snack that smiles back.
Yeah, boy. I feel like Kelani's a ladies man, you know. I feel like Kelani's a ladies man. What do you think? What's
Wow.
everybody staying quiet, eh? What's everybody staying quiet? Boy, Kelani, boy. Kelani, you see how much ups you have, boy? Nah, boy, Kelani, boy. This one of them one time.
That not good, eh?
That's not good. Well, we know Nikolai is the ultimate ladies man, you know.
I think I learned from Nikolai.
Nikolai, how come you have your camera off? Kelani and Nikolai, boy. Come on, level the camera off.
I trying to put my camera on, but like I don't know, boy.
Yeah, they can do some Michael Jackson moves, boy.
They tell me that they tell me I have no
By the
camera
way,
phone or something.
I was learning to moonwalk for the past week and I could actually start doing it.
Say that again.
Listen, I think I need to fix my camera. I see only black.
And Christopher and Gabrielle and Sasha with the camera, they look, Megan. I seen her so much people in class. I didn't know that.
I find in a serious sleeping, boy.
Good
I
job.
like
Just
Oh,
I'm
okay.
here.
Okay, so I hope I'll take all the screenshot, right? I hope I'll take all the screenshots.
yes,
All
sir.
right. All right, so we need to look at thermal expansion now in case this comes, right? So, earlier, we know the kinetic theory of matter. So here what I'm saying. In a solid, the molecules are held closely together. We know this.
Yeah.
When they are heated, kinetic energy is added to the molecules, making them vibrate faster. We know this. This causes the molecules to move apart and increase their volume. Again, we know this. But what is it called? It's called thermal expansion. Isn't this things we already know?
Yeah.
Yes, sir.
Alright, so before heating the ball, it could easily pass through the ring. But if I heat the ball, what's going to happen to the volume of the ball?
It would
They
increase.
get wider.
Okay, it will increase, and would it be able to go through the ring now?
Oh, no, sir.
No. So here what? In the exam, they could ask you to explain some phenomenons, right? So this is a phenomenon they could explain to them. Creaking roofs, but this is the one I would tell you to use. Power lines sagging on hot days. Think about it. Isn't the power lines made up? Isn't the power lines like made up of conductors?
Yes, sir.
Yes,
And
sir.
so, like, on a hot day, the length of the conductor is going to increase, so it's going to sag. You know what I mean? So, in a hot day, you might see power lines sagging, and this is due to expansion. This is a useful application of physics. If you're having trouble opening a jar because it's like too tight, you could run the jar over warm water because the lid, it would expand, and if it expands, wouldn't that make it easier to open?
Yeah.
Oh, yes, sir.
Yeah, physics, physics, physics. So, the more you know. And even in carbonated beverages, okay, if you take a carbonated beverage and then put it in the sun, what's gonna happen?
The molecules will
Uh,
vibrate too.
well, I
Well,
guess it would increase. I
The
don't know.
process will start to rise.
watch. Look at
Power
right
reaction.
here. Look at right here. When beverages get warm, remember in the beverages isn't there dissolved CO2 in the beverages? That's why they call it carbonated beverages.
Oh,
Yeah.
yes, sir.
Yeah. So the carbon dioxide bubbles expand and escape. They're gonna expand and escape, leaving it with a flat taste. However, in the cold, the bubbles contract and they stay within the drink. So I'll probably understand why they say keep the drink in the freezer.
Oh,
Yeah. All right, let me look at bimetallic strips, which is a prime application of thermal expansion. So, as the name suggests, bimetallic comprises of how much conductors?
2.
2.
Two.
Two.
Right, so the bimetallic strip consists of two strips of different metals which expand at different rates as they are heated. We usually use steel or iron and copper or brass. The different expansions force the flat strip to bend one way if heated and in the opposite direction if cooled. So you understand, the two of them would react differently to being heated or cooled. So like one might bend more and now cause it to bend in one direction. The other one might bend a bit less, so it might cause it to go in the other direction. So on top we have brass, in the bottom we have steel. So if you have it at some reference temperature, like at a normal temperature, it will be completely flat. If it's hotter than the reference temperature, the brass would expand more and its greater length pulls it on the outside of the curve. So guys, let me explain this. So over here they're saying brass expands more. So if the brass expands more, which length is gonna increase faster? The brass or the steel?
The brass.
Exactly, because they're saying the brass expands more. If the brass is expanding more, isn't this outer length here going to increase? But because this length here is increasing at a slower rate, it would actually pull it in this direction. I'm not sure if I could see it.
Yes, sir.
So Kelani, which one is going to expand at a greater rate, the brass or the steel?
No, the brass too, because it's expanding more.
So the length here it's gonna grow at a faster rate, right? And this one is gonna kind of like it's gonna expand at a slower rate, so it's gonna cause it to like get curved in that direction.
Oh, yeah, I see the connection too.
Because watch, this outer length would be what?
That with the brass.
And it'll be a greater length or a smaller length.
No, that would be a greater length 'cause it's expanding out more.
Exactly, exactly. So it would cause it to go in this direction because the inner one wouldn't expand at the same rate.
No.
And colder than the reference temperature, the brass contracts more. So if the brass contracting more, then okay, if the brass is contracting more, which length? Okay, contracting. If it's contracting, is it increasing or decreasing?
No,
Decreasing.
decreasing.
Right. So if the brass contracting at a greater rate, which would be longer, the brass here or the steel here?
The steel.
Exactly, and the steel is going to be the longer one, so it's going to cause it to pull up in this direction.
Right.
So let me give you an example of where this could be used. So over here, we have a circuit with a bimetallic strip. So in the event of there being a fire and this circuit gets hot, this bimetallic strip, it might get pulled in this direction and it would cause it to make contact. And that would allow current to flow through and complete the circuit. I'm not sure if you're seeing that.
So
Yes.
Okay, let's go over again. I didn't see the first time, so
All right, so Kilani, over here we have a circuit, right?
yeah.
But if you notice over here, we have a what in the circuit?
A contact.
Now, we have a break in the circuit,
Oh yeah, the detach, yeah, break, yeah.
a break in the circuit. Now,
Yeah.
here what I'm saying, with this particular circuit, if it gets heated, okay, imagine a fire alarm or something, right? Would you
Yeah.
want that? Okay, if there's a fire, wouldn't you want the alarm to go off?
Yeah.
So here what bimetallic strips are used in alarms or whatnot, or even in heaters, right? And when a heater reaches a specific temperature, what's happening to it?
When the heater reach a certain temperature.
Yeah, what's happening to it? I don't know if you ever realize it, but when the heater reaches a iron, you know, like the iron was iron it close with.
Yeah.
When it reaches a certain temperature, what's happening to it?
It would give off more heat compared to if it was.
Nah, like okay, try using a heater. You will see that when it reaches a certain temperature, it is cut off. Then it coming back.
Oh yeah, because it's like it can't go no more.
No, it's like a safety mechanism. It's like a safety mechanism. If it didn't have no safety mechanisms, it would just keep getting hotter and hotter and hotter and hotter.
Oh, so that's why you could only fill that kettle to max too.
Um, I wouldn't say so. But like the point I'm trying to make is, Kelani, in those kind of circuits where you don't want it to like just overflow, and you would need a mechanism to cut it off if the temperature reached too high.
Yeah.
So here what? If a circuit over here, right now, is the current getting to pass through?
Nah, because it have a break.
Have a break in the circuit here. There's a break in the circuit. Now, in the event of a fire, or in the event that the circuit gets really, really hot, this bimetallic strip is going to bend upwards. And if it bend upwards, what's going to happen?
Oh well, it would cause it wouldn't have a break in the circuit anymore. So
I would
the alarm would go off.
exactly. I wouldn't say it's a fuse, but it's a similar concept. A fuse is typically a thin conductor, and you'd apply it up in a circuit. And if the current is exceeded, you know, the thin piece of wire on the inside, the current rating would be exceeded, and it would melt, and it would cause a gap in the circuit. I guess it's similar concepts, but Kilani, here what I'm saying, right? If I heat the circuit up, the bimetallic strip is going to bend upwards, and if it bend upwards, what's gonna happen there?
It will make contact with the wire. It will pass through the wire.
Yeah. So you could use this as a heat sensitive switch in a sense. A heat sensitive switch. Because it only comes on at a certain temperature. If that makes sense.
Yeah.
So
If no
say
temperature being applied, if no temperature being applied, it wouldn't bend upwards.
it wouldn't. So you understand in an iron, in like an iron, right? Like it was an iron it close with. If the heating element reaches a certain temperature, it might cause the bimetallic strip to bend, and it might cause the circuit to cut or something. However, it's configured.
Right.
But like you understand, Kilani, once the circuit gets hot, this bimetallic strip is going to bend upwards, and that will do what to the circuit.
Make contact with the wire so it can pass through the other side.
Exactly, so it would complete the circuit. So I hope you
Complete
understand.
circuit, yeah.
All right, good. So in this circuit, the bimetallic strip, when heated, would bend towards the contact, allowing electricity to flow. This effect is used in a range of mechanical and electrical devices, such as thermostats and fire alarms. Because obviously, if there's a fire, you'd want the fire alarm to come on. So, Caroline, do you understand it completely?
Yeah, I understand it better now.
Right, so, cool.
It's like yeah, you could use it in like sensors, like any kind of alarm that you would need that you want to hear whenever something occurring.
Correct.
Like
Like if
it's
there's
like
a
for example, like a library, right?
wait, tell like Caroline talk there. Yeah, Caroline, say that again.
Like for example, in a library, if you steal a book and you're walking out, it would have like those sensors that would detect you.
Well,
I feel like
that would
better example.
that wouldn't be a heat sensitive switch, yeah? That wouldn't be
Oh,
a heat sensitive circuit. Like for this circuit to like be completed, you need heat. Because remember, a bimetallic strip relies on heat.
yeah. Okay.
Yeah,
It wasn't a good example, but it was just another way to think about it. Like yeah.
yeah. Yeah. I understand what you're saying. It's a kind of switch in a sense. All right, cool. So we covered a good bit of things when it comes to thermal physics. Um, let's see what else we could cover. Okay, good. We have to cover this question. While we're at it, all I want to do gas laws on in one time.
Yeah, no problem, sir.
Are they able?
Yes, sir.
You can see.
Well, here what? Before I do that, there's a question I want to do with you guys. This question was a really nice question. I would say it's more so on the challenging side. Who wants to help me with this?
Yes, sir. Wait,
All right.
before I go, anybody wants to go before I go? Seeing that I've taken most of the opportunity here.
Now go ahead now.
Oh,
Alright.
and by the way, don't forget to share up the YouTube live and thing. Don't forget to share it up. Let me just wait. Yeah, guys, don't forget to share up the YouTube live and thing. I'll go to a little 12 o'clock and thing. We on for physics. We go in. Right, I just sharing the YouTube live all over for anybody that didn't see it. All right, let me go. So, Nikolai, give it a read.
Yeah, Sandra.
What?
If I pronounce that right.
Where you get Sandra from, dog?
No, I never say Sandra. I'll
Hey,
try to pronounce the
I
Y.
can't be the only one I hear you, Sandra.
Nah, I
Anybody
never
else?
say Sandra. I say yeah, Sandra or something like that. I try to pronounce the Y.
Try it again. Try it again. Next thing, this is Nikolai wife name. Imagine Nikolai meets up a girl and like they get a connection and like when Nikolai actually she tell him her name. And when he tried to say it back, he say yeah soda yeah
Something like
Snowda.
that. Something like that.
Say how to say this name correctly. What if this is your wife name?
You're slow now.
Nikolai, come on, man.
So I'd say that word for the time being.
Try it again. Then. Try it. Yeah.
Yeah. Uh
English. This is English vibes. This is English vibes. English vibes.
Yeah,
English vibes, Rajiv. Nikolai, we could do it. Say shh.
shit.
And this is what?
Ora.
Right. So put it together.
Shoulda.
Right now, put this on this together.
Yeah, shoulda.
Yay!
You shoulda.
W
You shoulda. You shoulda.
So
W.
this is exactly what
So,
C-sectors
so
do
I
to people.
initially thought of
Okay.
that. So I initially thought of that and I thought it was weird. So I just changed it.
Oh yeah, yeah, sure. Yeah, so yeah, sure. That prepares.
Yeah, shoulda prepare some lime juice on a hot day. She adds 80 grams of ice at a temperature of 0 degrees Celsius to 0.32 kilograms of lime juice. The temperature of the lime juice decreases from 29 degrees Celsius to 8 degrees Celsius, and all the ice melts. Latent heat of fusion of ice is equal to 3.4 times 10 to the power 5 joules per kilogram. Specific heat capacity of water is equals to 4.2 times 10 to the power 3 joules per kilogram to the power of minus 10 degrees Celsius. Calculate the energy required to melt 80 grams of ice.
Yeah. So Nikolai, let me understand the facts here. So Yashoda is preparing some lime juice on a hot day. She adds 80 grams of ice at a temperature of 0 degrees Celsius to the 0.32 kg of lime juice, right? So Nikolai, let me do a little diagram, right? Nikolai, you there?
Yes, sir, here.
Right, so this is the lime juice over here, right? This is the lime juice. Now, before she added the ice to the lime juice, what was the temperature of the lime juice?
Eh, 29.
Right. It says it decreases from 29 degrees Celsius to what?
8.
So it was originally 29 degrees Celsius. Now, when she add the ice into this and the ice completely melted, it turned to what temperature?
8 degrees.
And this is after the ice what?
Completely melts with the lime juice.
Right. So Nikolai, and what is the mass of the ice?
It was 80 grams.
It was 80 grams of ice. We had to convert that to.
The kilograms.
So immediately, let's convert that to kilograms, right? So that will be 80 gram, 80 divided by what?
1,000. Which is 0.080.
0.080.
Yes, sir.
You sure?
Isn't it 1,000?
Let's verify that. 1, 2, 3. Yeah, correct. And they want us to find the energy required to melt 80 grams of ice. If we are talking about melting there, Nikolai, melting means that there's a change in what?
Phase. Well, no, temperature.
No. Melt. What does melt mean, Nikolai? Melt.
You change it from one state to the other.
Right, change in state. Right, so Nikolai, what formula should use here?
Latent heat of fusion.
Right, so E would be equal to.
MLF. Common F.
Everybody with me so far, like they confused,
Yeah.
Understood.
right? So Nikolai, what was the mass of the ice?
The mass of the ice was 80 centimeters. I mean, why say in centimeters? 0.080 kilograms.
And what is the latent heat of fusion? They gave us that. What was it?
3.4 times 10 to the power 5.
3.4 by 10 to the power 5. Yeah, are you okay with that?
Yes, sir.
Plug that into the calculator and let me know what you're getting.
I got 27,200.
Anybody else get that?
Yes, sir.
Yes, sir.
It was 24,000.
27,200.
27,200
And where's the units for that?
joules.
Joules.
Everybody understands that, right? Because it's energy.
Yes, sir.
Alright, so that first question was how easy?
That was reasonably good. Well, I just say good.
Easy or hard?
Would
I
say
wouldn't say
easy.
I would say that's easy, right? So now, after today, anytime you see words like melt, you know what you're dealing with that change in what?
Change in state.
You're dealing with that change in state. Good. And if you're dealing with that change in state, and we're talking about ice, ice would turn to what? And it's melting. Ice would turn to what?
Liquid,
Liquid.
Ice would
water.
turn to liquid. Ice would turn to water. So we're going to use E is equal to MLF. The mass of the ice was given to us in grams. So you have to convert it to kg. So we divide it by 1,000. And we know LF is 3.4 by 10 to the power 5. They make a little mistake here. What did they forget to put over here, guys? Since it's joule per kg, what did they forget to put here?
Specific latent diffusion.
Yeah, they forget to put specific.
Specific.
Yeah, boy. They forget to put specific because it's per kg. Right. So, Nikolai, read part B.
The energy gained by the melted ice.
Right. So, Nikolai, I really want to know if you can figure out this one.
Well, we had to calculate the mass of the ice with the lime water.
Nah.
Oh, the energy with the ice with the melted water.
Okay, so let me hear what you're suggesting. What are you suggesting then?
Well, since we're looking for energy, we had to look for energy. Well, okay, so we're looking for energy, which we're using E is equal to MC delta. No, MC delta theta.
Okay, so here what? Do we know what the mass is? Do we know what the mass of the ice is?
Yes, sir.
Again, I want to stress this, right? In this entire question, you are just dealing with the what? What are you dealing with?
The ice?
Yeah, you're dealing with the ice, right? What is the mass of the ice again?
0.080.
Oh, if I lose all that any points, I'll able to tell me, right? What is the specific heat capacity?
3.4 times 10 to the power 5.
It's so easy to make a mistake, Nikolai. Where you just tell me what's the specific latent heat of fusion.
Oh, my bad. 4.2 times 10 to the power 3. I was looking at the first thing on top. My bad.
Now here's the tricky bit. How are we gonna find the change in temperature? What do you guys think the change in temperature is? Let me see how bad it is, right? We're talking about the ice.
I
The
feel
0
like it's
degrees.
8 degrees Celsius because it goes from 29 to 8. So I'm thinking 8 degrees Celsius.
Who else agrees it's 8 degrees Celsius?
Well, the energy gain will be the heat loss from the hot water. So I would say so. Yeah.
Okay, I would say it's 8 as well. And if you're confused, right, let me explain something. So, Nikolai, at the start, we started off with ice, correct?
Yes, sir.
What was the temperature of the ice?
0.
And then this ice would have turned to what?
Water.
And this water would have be at what temperature?
Also be 0.
Now, here's the tricky bit. When you add the ice to the lime juice, it would melt and it would acclimate to what temperature? Let's read the question. When I added the ice to the lime juice, what happened?
It decreased the temperature of the lime juice from 29 to 8 when all the ice was melted.
Exactly. So, Nikolai, hear what I'm saying, right? Nikolai, hear what I'm saying. Oh, hear what I'm saying, right? When I put the ice in the lime juice, so I'm going to represent the lime juice by this color over here. So this is lime juice, right, Olia?
Yes, sir.
Somebody unmuted. All right, yeah, Kiana was unmuted. Kiana, you mute. Oh, yeah, good. Yeah, so here what? I'm going to represent the lime juice by this color over here, right, chat?
Yes,
And
sir.
I'm gonna represent the ice via this over here. So after I put the ice in the lime juice and it completely melts, the temperature of the lime juice and the liquid water combined is what?
8 degrees?
Yes. After everything melts and it switches up and it acclimates, the final temperature is what?
8 degrees.
8 degrees.
So if we're looking at the initial and then the final, the ice would melt, turn to water at 0, and then lastly, when it's in the lime juice and it's now liquid water, and everything is mixed up, it would be at what temperature?
8 degrees.
Yeah.
Yes. This is the part where a lot of students would not figure out. But here what I'm saying, guys, isn't the ice fully melted and mixed with the lime juice?
Yes, sir.
Mhm.
So, Kelani, if the lime juice and the liquid water are combined, then the temperature of the entire thing for the both of them is just what?
Just 8 so because it decrease.
Exactly. So the ice will be from it'll be ice at 0, then water at 0, then water at 8 degrees Celsius.
Yes. Because it
Let
will
me
just
check it.
when the ice go in the water, so it wouldn't just magically turn to 8 one time. It have to go through a little process.
Right. Now, I'm seeing a lot of people saying 21. That's incorrect. If you tell me 21, that would be wrong because that is talking about the lime juice. Are we talking about the lime juice? When you read the question, are we talking about the lime juice?
No, sir.
So, Michael, if you said 21, that would be wrong. That would be the change in temperature for the lime juice. But, Michael, we are talking about the energy gained by the melted ice. So, we're not talking about the lime juice, we're talking about the ice. Hope you understand that, Michael, and anybody else that might be looking at this. I'll go it over one more time. You put the ice in the lime juice, it completely melts, and when everything is mixed around, what's the final temperature?
8.
8. And that would tell you the final temperature of the lime juice and the.
Ice.
Yes, because that's the liquid water and the lime juice. And both of them at 8 degrees Celsius because it's at an equilibrium point.
Yep.
Yeah. So this is the part where a lot of students would not understand. They'll put 21 on it, I get it wrong. Virginia, you there? I'm not here in Virginia. But guys, are we talking about the energy gained by the lime juice or the melted ice?
Melted ice.
Ice.
So would you go and put the change in temperature for the lime juice here then?
No.
No, sir.
No, I hope all you're seeing, I saw all you're seeing the light at the end of the tunnel there. You're not going to say 29 minus 8 because that would be the change in temperature for the what?
Lime juice.
I mean, lime juice.
Lime juice. And are we trying to find the energy gained by the lime juice?
No,
I mean,
sir.
maybe technically, nah. Technically, it will be energy lost by the lime juice, right? Because the ice is going to take the energy away from the lime juice.
Yes,
But
sir.
anyways, it's going to be 8. I hope all you understand why. Because the final temperature of the lime and the ice when it melts is 8. Right, so what would that be? Somebody tell me.
Oh my gosh. Man, I literally cancel everything. I'm gonna do it over.
Like Virginia fall asleep there, boy.
I got 2,688.
Anybody else get that? 2,688?
Yeah, it was
Sir.
2,688 joules.
Cool. So to go from ice to water, it was 27,200 joules. And to go from 0 degrees Celsius to 8 degrees Celsius, it was 2,688 joules. So the whole process is how much energy? The whole process is how much energy?
So it will be that
The
plus
adding, yeah,
So what would that be?
29,888.
yeah, I got the same thing.
And would this be energy lost by the ice or energy gained by the ice?
Energy gained.
Gains.
Yeah.
Wait, I 6 marks there already? Well,
So the energy gained by the ice is what? What is 27,200 plus 2688?
I got 29,888.
29,000.
29,888.
Wait, I had real background noise there. 29,888.
188, yeah.
Okay. And that will be in joules, right?
yeah.
Yes, sir.
So here's the part that a lot of students don't connect. Where did the ice get the energy from, boy? Where did the ice get the energy from?
The lime juice, sir.
Yeah. So the energy gained by the ice would be the equal to the energy what?
Lost by the lime juice.
Yes.
Yeah, physics really making sense, boy.
Because I mean the ice had to get the energy from somewhere, right?
Yes, sir.
But here, question, sir. And when the ice gains energy from the lime juice, when you add up the total energy, and that would result in a mass increase.
So
Like
that get
say I had it, all right, so like you see like what the ice gaining energy from the lime juice, right?
right.
When you add up both energies, so like you see what we get 2,000, 27,200 plus D2688, right?
Mm-hmm.
And the total energy, since it's more than the initial, it would have a mass, like an increase in the mass.
Okay, I hear what you're saying. The mass of the total thing would increase, but we are treating the two independent of each other. And why am I saying that? I'm saying that because the lime juice, okay, do you think the lime juice will have the same specific heat capacity as water?
Nah, it'll be different.
It could be different. Do you think the latent heat of vaporization or latent heat of fusion for lime juice would be the same for water?
Nah, two different things.
So we need to consider it independently of each other. We're not going to add the masses,
Yeah.
right? But the final mass would increase,
Yeah, because
right?
ice has caused liquids to go up now, like breeze.
So I hope you understand this. The energy gained by the ice is going to be equal to the energy lost by the lime juice. So, watch. What you call it? We call it. What's the answer for part C?
21.
It'll be 29888. You understand?
Yes, sir.
Yes.
So here what? Kelani, I wait help me with part D now. Since he was talking about the mass and yeah, talk to me.
You could go back to the part B there for a second.
Sure.
Right. So for part B, right, the answer will be 29,888, right? Because and that
Oh
will
no,
be the,
nah. He's talking about this part B over here.
yeah.
Nah. So like they want you to say the energy gained by the melted ice. So let me explain.
Oh,
So
just what
over here, this is the energy gain from going from ice to what?
ice to liquid water.
So this over here, this is the melting process. And
Yeah.
this over here would describe the energy gain by the melted ice. Because it would be water at 0, but now it's water at 8. So it gains some energy. This is what they're talking about. This part over here.
Thanks, sir.
But the total energy would be what?
The 29,888.
Now let me explain something. The ice gaining energy, but where's the ice gonna get the energy from?
The lime juice.
Exactly. It's gonna pull the energy from the lime juice.
Yeah.
Good. So that's why I'm saying the energy lost by the lime juice is the total thing. I wonder if you understand.
Yes, I understand that.
Alright, so Kilani, help me with part D. This is how bad it is.
The specific heat capacity of the lime juice. So
So what formula should use one time? Tell me one time what formula should use.
E is equal to mc delta theta, sir.
And I gonna put CG, because if you put C alone, well, that kinda indicates specific heat capacity of water. Second part is CG.
Yeah.
All right. Do I know the energy? Okay, let me ask you. What do you think I should put for this?
It will put the the 27,200.
Nah.
Oh no, sorry. The 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 29,888.
Good. Because isn't that the total amount of energy? Isn't that the total amount of energy lost by the lime juice?
Yeah, that's the total energy lost by lime juice. Makes sense.
Right? Here what? A lot of students might be tempted to add the mass of the ice and the lime juice, but that's wrong. If we're dealing with the lime juice, then we're specifically talking about the mass of the
Lime juice.
exactly. So can you remind me what was the mass of the lime juice?
That was goes 0.32, yeah, 0.32 kg.
Right? Do I know the specific heat capacity of the lime juice, CG?
No, that is unknown, sir.
No. Do I know if no, okay, now we can talk about the lime juice, right? If we're talking about the lime juice, what was the change in temperature for the lime juice? Look at the question.
Yeah, it going from 29 to 8, so you have to minus it.
Correct,
You'll
correct.
get 21.
So I know that the energy lost by the lime juice was that. I know that this is the mass of the lime juice by itself, and I know that this was the change in temperature experienced by the lime juice
Yeah.
because I added the ice. So a way to multiply 0.32 by 21 and let me know what you get.
All right, hold on. I get 6.72, sir.
6.72.
Yeah.
So if
Yeah,
I
well,
wanted to find
we
6,
have
7.
we have one unknown, so we could literally just make that is the formula.
So I
So
divide them both sides by
divide both sides by 6.72, sir.
That's it. Yeah, cool. One second. All right, yeah, let me continue. So, the specific heat capacity of the juice would be what?
I get 4,447.62.
4,447.
0.62.
And the units could be joules per.
Joules per kg.
Yep. Joules per kg, degree Celsius.
Degree Celsius, correct.
And if you're confused, to get this, we had to divide throughout by m delta theta, right?
Yeah.
So it'll be energy, which is joules, all over the mass, which is kg, and we had used degree Celsius. So the units could be joules per kilogram degree Celsius.
Yeah.
That's it. So Kelani, when you're dealing with these types of questions,
yes, sir,
you're treating them like independent of each other. You're not gonna add no mass on thing, You're not gonna do that. You're not gonna do that. You're gonna add no masses.
No, I was just thinking about it logically, like on a broader perspective.
I see. Well, I wonder if they could probably ask you a question. Find the specific heat capacity of the lime juice and the ice. I don't know if I don't know if they'll ask you that though.
These are the typical way that this is bring these questions.
Yeah.
Mostly dealing with energy and stuff.
So the one if you fully understand this question. Is that
Yeah,
tricky one?
the procedure wasn't too bad. It was just a level of understanding that we not is like you're treating them as you say independent of each other. So you just have to understand that.
Good.
And yet,
And we're not gonna add
make sure I don't confuse the units.
And just like when we talk about the change in temperature here, I didn't put 21, I put 8 because we were strictly talking about the ice.
Yeah, yes, I had to be careful with them thing too.
And because like the final temperature, everything would be 8. So long story short, when the ice fully melts into water, the final temperature of the water with the lime juice will be at 8.
So
Yeah, so this is a nice question.
they Collins workbook.
Yeah, I think Terry make this, Terry
Yeah, I
make
think
this.
so. I'll try some questions, yes.
Yeah, big up Terry. All right, so let me do the question in 2025. Then we go tackle some gas law questions and we call it a night. It's 11:11, make a wish.
All my ones in CSEC.
You're not supposed to say the wish out loud, Nikolai. I don't think it's work like that.
Don't matter, don't matter.
Wait, boy, real WhatsApp messages. Risha is supposed to tag me on the Zoom, boy. It's supposed to tag me. Supposed to tag me, boy. Right. Yeah, let me tackle the question from 2025 now. Any of you guys try the January 2026 physics papers
I
yet?
already did.
Nah, I've been honest with you, I didn't do it so.
It was easy or hard?
Actually, it wasn't. It was mid.
It was mid.
Yeah.
In the 2025 physics paper, it only had one source question. Everything else was really easy. The only source question was the first one with the graph. That was the only source one. This is the January 2026 paper. So I want to do the 2020, whole of 2026 paper and the whole of the 2025 paper. What's all there? I say once all here, we go in, once all here, we go in.
Yes, sir.
The amount of people I was asking me to do live on thing, I thought I had more people on TikTok and YouTube, Look like these people wasn't serious, but right. I want to help me with this question.
I don't mind, sir. Don't mind if I do.
I'll hear Nikolai say that. Don't mind if I do. Like a Texas person. Nikolai, if you don't get all the subjects, I'll cry,
I
The
will
amount of
cry
work
with you,
you just
sir.
be
Sir, I will cry with you, sir.
Nikolai, if you don't get a distinction in physics and I probably wouldn't say a distinction, but like, if you don't get through, I'll cry.
But poultry is paper ones. Nah, I wouldn't say poultry, but it's just like the surety.
Though I don't realize that I ask Spanish people want them more and they wish me luck, eh?
Oh, yes.
Hey, good luck, yes?
Hey, boy.
Who here has Spanish, boy?
Definitely not me, but 5 years in a couple of days for just one exam? That's crazy.
Nah, the paper one ain't gonna be too bad. But I really trying to get some info.
Oh, it's paper one.
Yeah.
Yeah, well, 25%, one of them correct.
Oh wow. That's such good help. When in doubt, use C, boy.
C? I thought it was D.
C. Always the right answer, sir.
Then if it was, then it'd be 100% chance.
But it has some questions you obviously know the answer, but question that you're really not sure, so there's always CSV answers.
And
Okay.
then there's some questions that have the answer, but it have two answers with it. So you have to pick which one more accurate. I
That's
would
true.
say that's for like biology. Like biology would have the answers, but it's just one tiny thing you gotta look for that will really tell the difference.
Anyways, are you ready? Are you ready to finish the question? I hear
Yeah.
they're
Yes, sir.
talking on.
Yeah, sir, we waiting on you now, sir.
After you
Oh,
finish
I
this, I
hear.
go bust out.
Alright, no problem.
Like,
Well, I feel like I should just do thermal physics tonight. No, no, I shouldn't do them gas laws tonight.
Yeah, no problem, sir.
I just don't want to stay up too late now because the exam
No,
tomorrow.
no problem. So an electric hot plate rated at 240 volts and 3.5 amps is used to heat 600 grams of liquid. The liquid is heated and its temperature is recorded at 20-second intervals. The results obtained are shown in table 1. So immediately, as seeing that the voltage is 240 volts, the current is 3.5 amps, and I'm heating 600 grams of our liquid. So if anytime I see them mention voltage and current, a formula should come to mind. What is V by I? V by I tells me what?
Power.
Power. Yes.
Yeah.
Power is equal to V by I. So I show any other question, they want me to find power or something, so you just know that.
Sure.
And this 600 grams, we'd have had to convert it to what anyways?
Kilograms.
Kilograms, sir.
So that'll be 0.6 kg.
Yes, sir.
All right. Let me do this graph quickly. Now this graph was real weird, eh? This graph was so weird. Weirdest graph I ever see ever. So let me explain. Using the data recorded in table 1 and the grid provided in figure 1 on page 5, plot a graph of temperature against time. So by the way, guys, what we have over here is a what curve. See if I can tell me.
Okay, yeah, curve.
Yeah, this is a what curve, guys?
Heat curve.
Yeah, this is a heat and curve.
Ah,
We just do that.
the heat, like the words literally heat over there.
Yes.
Yeah, watch Nikolai. As time increases, what are we doing with the temperature?
Temp, it increasing. Nah, we don't watch that one, sir. That point, we don't have that point on the graph, sir.
I find like you're
No.
zooming on that point again.
Now, here's what's weird. What did it say? They said draw the line of best fit through the last 5 points. That is from t is equal to 120 to t is equal to 200. Very sus, guys. Very sus. This is not sus.
So let me just say, let me forget the rest. So what's the point of doing the rest?
That's what I'm saying, right? Where's the point? Let me answer this question first. So, Nikolai, we plot on a graph of temperature against time. So, temperature, we're on which axis?
Why?
And time, we're on the x-axis.
Yes, sir.
Let's come up with our scale fast. So, here what, right? This was a bit weird because in earlier custom plotting vertical graphs, portrait
Yes, sir.
graphs.
Yeah.
If you did plotted portraits, it would have looked like this, which is also correct. But I feel like more people might understand it's if I do it landscape. But this is also correct.
What?
Just thank God at least this question not gonna come again this year.
Hey, expect the
Hello?
unexpected, you know. Next time
Right,
this
so
come on, you jinx yourself.
right, so let me do this first. This is temperature. Temperature is measured in degrees Celsius. This time over here, I'm measuring time in seconds. So Nikolai, help me come up with a scale on the x-axis now. Time going on the x-axis.
Yeah, going up by how much we have? 18. 18 blocks for the X. So every one block is 20 centimeters.
You want to say every one block is 20?
Yeah, because I don't think, well, if you go like 10, you could need like 20 blocks to make the 200, which we don't have that much space thinking if we go in landscape.
So you want to say that every 2 blocks is 20?
No, one block.
If you use 1 block is 20, I feel like the graph will be too like, watch. 20, 40.
No, that's not the X in it. Oh, wait, but that's the Y. No, that's the X. Oh my goodness. Never mind. 2 blocks is 20.
Remember, Nikolai, this graph
One
was
block
kind of
is 10.
weird. This graph was kind of weird.
So I
Nikolai,
studied the temperature kind of thing.
let me explain something, right? If you go to do this graph like this, it will be looking very, very weird. Because this is how they bring the graph for you. This is how they bring the graph, you know.
But like the y-axis on the right hand side, boy. Well,
Yeah, so like if you was doing it like this, you'd have to put the values increasing in this direction. Like 20, 40,
what?
60, 80, 100, 120, 140.
No, not on the other side.
Yeah, like, okay, and when you're doing graphs, and it's typically like this,
Yeah.
Yeah.
yeah, I think I'll understand why I say it was a weirder graph.
Like they make a mistake in the printing room or
I don't know, but I'll understand why the preferred method is really horizontal.
Yes, sir.
Let's see it or no? Because it's real weird. You just never really deal with a question like this.
yeah, I think I would have put my paper horizontal too.
Right, so let me do this quickly. So I can't tell you this scale fast. I feel like every 2 blocks is 20 will work. Yes, if they do something like this for you, just know it make more sense to do it horizontal, right?
Yes, sir.
All right, cool. Now we need to come up with a scale on the y-axis. Nikolai, you have any suggestions?
Well, I see we're going up to 70, so every 2 blocks is 10.
That's a good suggestion. So 10, 20, 30, 40, 50, 60, 70. All right, cool.
Yeah.
And well, this would be 80 over here. All right, so the first point is 0, 28. Okay, no problem. So 0, 28, that would be
2
okay.
blocks
Just to make sure nobody is confused. Watch. We have 10 small blocks is equal to 10. If 10 small blocks is equal to 10, then one small block would just be 1.
1, yeah.
So 28 would be 2 blocks below 30, right here.
Sir.
Then we want to plot 20, 28. It's gonna be right. It's gonna be right here.
Sir. Yeah.
I realize I make a mistake there.
Yes,
Then
sir.
we have 40, 30. 40, 30 is going to go right here.
Yes.
Then we have 60 to the 4.
Just 1 before the half.
I don't sleep, guys. I don't sleep. Then we have 80 to the 8.
2 before the 40.
Then we have 143.
That's 3 up.
Oh, make sure you subscribe to Matt Vibes, you know. Make sure you subscribe. Don't forget.
Yeah, do this, watch the video and do subscribe. Subscribe. Like. And share the video.
Otherwise, Nikolai will come for you on your sleep.
Yeah,
Make
you know
sure
that's
that physics and maths going in our brain. And when you wake up with sine and cosine.
The signs were always there.
Exactly.
Just didn't take it on.
Nah, somebody
140, 160. 160 is 59.
Yeah. That's 1 before the 60.
That's over here, right?
Yes, sir.
Then 186, 7. Right here.
So the amount of graves you in already, and you still alive somehow?
I am a zombie. I'm never dying. 274. 74 will be right here. Bam.
Yes, sir.
Now they said draw the line at best fit through the last 5 points. So we had to count the last 5 points. So 1, 2, 3, 4, 5.
I like to use the last point and the first point and just draw lines using those 2 points.
But hear what? If you do this in the exam, big wrong. No. What did they say? What did they say?
Truly 5 points?
Yeah, they said draw the line at best fit through the last 5 points. So Nikolai, that's why I count the last 5 points. You understand?
Yeah. Oh,
Real
well,
weird, right? We're
no,
real weird, right?
no, let's say I use the first point, which is the 200, and the last point, which is the 120, and draw the best fit through there.
Okay, yeah. The 120 is the
That was-
fifth one. Yeah. That makes sense. Tell me what you think is a good best fit.
Well, you're not going past yes, somewhere, right? Nah, the 120 you're blocking it with the ruler.
See, boy.
Yeah, just tell the by the 120 and we should be good.
Feel that's fine, do you know?
Okay.
Remember, our best fit had to like be in between. It's kind of like average.
All right.
Come on a second. Do I like that? Do I like the way that looks?
Yeah, it looks fine to me. I mean, it passing through the points. Well, passing through the points are best fit. When does it pass through? And that means some of them had to be touching as well.
Nah, it's just like okay, let me show you what I mean, right? So Nikolai, imagine this was my data, right? Then my best fit would be like this. It don't really have to pass through. It's like average, if that makes sense. So this was the graph when I draw it over here. But like I had to say like I didn't recommend this because they say like draw the line at best fit for like here to here now. So like I say probably shouldn't I extend it. So I recommend this. I'm gonna call you okay with this.
Yes, sir. I think for this particular exam, I remember we was getting this on a test, but I draw the curve, but I put the line which was best fit through the 5 points.
Yeah, if you want you could yeah. Because it's a heat and curve, right? It's a heat and curve. Kelani, you okay with this?
Yeah.
Yeah, sure.
Yeah. It's just like you just had to watch the last 5 points and draw the best fit.
Alright, cool. So now we can answer the question. Hence calculate the gradient of the line drawn in A part 1. So I'm looking for some nice points on this. I've seen some nice points already. Now here what? Can I use this point over here to find gradients?
No, sir.
Nah, normally
I
you
could
have to
use
use points that not on the line.
You said I had to use points that are not on the line?
I mean, oh no, I said that wrong. Sorry, I mean to say normally it is use points that it didn't plot.
Yeah, I had to use points on the line. So I could use this one over here. This look like a nice one. That looking like 130, comma 50. I could
Sir,
potentially yeah, Nikolai.
if they went past the line, like right, like when past the 5 points, is that still allowed or would that be considered wrong?
No, that's allowed, but I wouldn't recommend doing this. because it would kind of be a bad representation of what it actually is. So
Right.
let me show you what I would recommend any exam. This is why I would recommend any exam. You see how this part looking like a curve?
Yeah.
Probably recommend that you do something like this. Something like that. Because that's what it actually is, you know. Because you probably realize that this part kind of curves and this part over here is kind of like a line. So I would not recommend drawing this thing like all the way back there. No. What really happening is you have a curve here and then this part is straight. So pick points like here and here. Right? So are we seeing any other nice points?
Oh, are you right close to the first one?
Well, see that point over here?
Yo,
Potentially
the
use that.
triangle kind of small.
Say that again?
The triangle is kind of small.
Yeah, so maybe we could.
I don't like my teacher from school told me was to get the triangle as big as possible.
It doesn't really matter, you know, because gradient is a ratio between the rise over run, so it technically shouldn't matter.
Oh, okay. Well,
So I could
hi.
pick this here because no matter how big the triangle is, the ratio is going to be the same regardless, because you know gradient is just a ratio between the change in y over the change in x. It doesn't really matter. So over here, I see, and this is 170. I don't know why did it say that. And then this looking like
74. No,
74.
64. My bad.
So I could call this x1, y1, call this x2, y2. So the gradient would be y2 minus y1. So that'll be 64 minus 50 all over what?
170 minus 130.
They didn't want me to call the gradient anything specifically. They wanted me to call it g. So here I will say, I would say that g is equal to y2 minus y1. There's a call for the formula, eh?
Of course, there's your max there one time.
And I would change this m to a g because that's what they want me to call it.
I got 7 over 20 as my answer. I don't
Anybody
think
else
they
get?
specified. I don't think they specified it if they want it as a decimal or a fraction.
Well, anybody get 7 over 20? Something close to that? Well, I gain 7 over 20.
Number 20. Wait, the 5 marks for calculating gradient done?
And we had
Yeah.
to pay units. We had to pay units, you know. We had to pay units, guys.
Oh yeah,
Um,
but
on the y-axis, we measure in degrees
temperature.
Celsius, and on the x-axis, we will measure in seconds.
Seconds.
So when you're writing the units, it's going to be degrees Celsius per second. And that's 7 over 20. I'm going to write it in 2 decimal places. So what would that be?
0.35. That is all it gave me.
How many follow you get at 0.35 degrees Celsius per s?
Yes, sir.
Now, when I did this question initially, I got 0.33, which I believe is the exact answer you want, right? That's the perfect answer. I believe. I believe that's the perfect answer. You can
Okay.
see why. But again, 0.35 degrees Celsius per second over here. All right. So then they're saying, look at Collet Nikolai. They always calculate the power of P of the hot plate in watts. Remember at the start, they give me voltage and current. So power is equal to what again?
IV. Current multiplied by the voltage.
Yeah, so that would be 240 multiplied by the current, which is 3.5, which is what? Oh, and by the way, when you do a graph in physics, you're supposed to put the scale, eh? I forget that. You're supposed to put the scale on the
And the
there's a
topic.
label. Yeah, you're supposed to put the label it too. So this will be the graph of temperature in degrees Celsius versus time in seconds. And the scale, I saw a custom forgetting that in maths, eh? What was the scale we used, boy? 2 centimeters.
Centimeters for 20 seconds.
So on x-axis and the y-axis, we had said that every 2 centimeters,
10.
10 degrees Celsius. Oh yeah, be careful, be careful. If you want to get full marks in physics for your graphs, you need to label the axes and state the units for both of them.
I believe like that's like a 8 or a 5 max for that.
8 marks, 8 marks. You had to put the scale and you had to put the title, right? So guys, when you're doing a graph, you name each axis, you put the units as well. You put your scale, you put the title. That will give you full marks. So don't do like me and forget that. What's 240 by 3.5?
I got 840.
Anybody else get 840?
Yes, sir.
All right, 840 watts. Cool. Did I forget anything? No, I didn't. And please don't forget to pay your units, right? So like a mark for the formula, mark for this, and a mark for the units. Yeah. Assuming that all energy from the hot plate is transferred to the liquid. So Kelani, remember how we talk about if the liquid wasn't properly immersed? You see in
Yes,
over
sir.
here, you see in here, Kalani, they're saying assuming that all energy from the hot plate is transferred, implying that it would be completely immersed. Just making the connection.
Oh, yeah.
Calculate the energy in joules absorbed by the liquid in the last 80 seconds. So Nikolai, give it a chance. They want me to calculate energy, right? They want me to calculate energy. I'm not sure if you're seeing that.
Yes, sir.
So if they want me to find for energy, do you know any, and we just find for power, Nikolai. Is there any formula that you know that involves power and energy? And if you notice, in the question, what they're giving us?
Time.
They're giving us time.
P is equal to energy over time.
Right. P is equal to energy over time. And we want to find for what here?
E. So we substitute. So we put E as the subject of the formula. So it'll just be power times time, which is equal to E.
So I can multiply both sides by T. Right. So they said so they said assuming that all energy from the hot plate is transferred, calculate the energy in joules. So we're going to be using what power? What power are we going to use, Nikolai?
The 840 watts.
And what time? They said in the last 80 seconds. So that'll be a time of what?
That would be a time of, oh my goodness. 6 is
And
special
what?
number 200.
Why the number so common, boy?
I don't know.
Kilani, let me know if you understand this.
Yes, I catch it. You just rearrange to make it easier to make the formula.
Right, cool. Because here what? In the last question we find for power. In this question they mention energy and they give us time. Power, energy, and time. P is equal to E over T. Fix up.
So I hope they bring these questions in the exam, sir.
I hope so as well. Is that easy? 15 marks. Alright. For the liquid, calculate the value of C, given that the power P is related to the gradient by the equation P is equal to mCg, where m is the mass of the liquid. Express your answer to 3 significant figures. No problem. So they're telling us that the power is equal to the mass times the specific heat capacity times the gradient. And they want us to calculate the value of C. So we got to make what the subject?
C.
You want to plug in everything and then divide, or what you want to do?
Plug in everything because we just to finalize stuff. So
So what's
power,
power? What's the power?
840 watts.
What's the mass?
I believe they gave us that in the beginning.
Yeah, they did. 0.6 kg.
0.6.
Right? What was we actually trying to find for that?
Gradient was what we found. I mean, G is what we found as gradient. 0.35. We locked in for CSEC physics.
For sure. So what is, so we could simplify that with 0.6 by 0.35.
I got 0.21.
And so what would I do to find for C now?
Divide by 0.21 throughout the whole equation. So 840 divided by 0.21.
You should get something.
I get 4,000. I get 4,000.
Let me verify that. You should get something really close to 4,200.
Oh, well, then yeah, it's 4,000.
Because you understand the actual answer is supposed to be 4,200, right? Because we're talking about the specific heat capacity of, well, I suspect they're talking about water. Because you should know, like, the specific heat capacity of water is 4,200.
I'm
Right.
guessing that the next question could be where compare the condensed milk, the milk or something else.
Now, let me just check something. Give me a second. Wait, where we get 0.21 from? Where we get 0.21 from? Oh, yeah, when you multiply.
By the 0.6 and the 0.35.
Let me just verify something quickly. Okay, that's the answer we get. Well, work with it. They get that correct. Yeah, that's fine.
Yeah. I
Mark a
believe the
pencil.
next question was a 1 mark for the comparison of that. Huh? Okay. I believe where I work out a question like that already. And then the next question after that was compare that results to the given information in the table. And you will just have to put in milk.
Oh, no, I don't know about that one. So C was equal to 4,000, and the units for this would be what? So it's a specific heat capacity. What that would be?
Joules per
Joules per
kilogram.
kilogram degree Celsius.
Yeah.
Now, here, in the question, what temperature do we use?
Degrees Celsius.
Yeah, so it will be kg degrees Celsius.
Sir.
All right, so how you feeling about thermal physics, chat?
Well, I mean,
Let's
I
how to
think
remember this for CSEC.
I will practice the like you see the question we know already from the workbook, so I think once we could master them, we could answer any thermal physics relating to like specific heat capacity and those stuff.
I would. I think you'll be fine. I think you'll be fine. I see somebody on YouTube ask me how I find a gradient. Guys, it's the same thing in maths. You just take 2 points on the graph, and okay, I'm running back again. So we're looking for 2 nice points that are on the best fit line we just draw. So I see this was a nice point. So I read off the x value. The x value here is going to be 130. So it's 130. And the y value is going to be 50. So 130, 50. Then another nice point that is on the line is over here. So this would be 170. And the y value are looking like 64. So 170, 64. Now when you find any gradient, it doesn't matter which one you label x1, y1 or x2, y2, but you have to label something. So I decided to call this x1, y1, and I decided to call this x2, y2. If you had done it the other way around, that would have been completely fine. So how do you find a gradient? To find a gradient, it is y2 minus y1 all over x2 minus x1. So what was our y2 value? Well, we decided to call that 64. What was our y1 value? That was 50. Our x2 value was 170. And our x1 value was 130. So when you work this out, you should get 7 over 20, which is approximately, well, that is 0.25 or 0.35. And that's where I had gotten Nikolai.
Yes, sir.
Right. Now, it doesn't have to be G, right? But the question will specify. In this question, it said calculate the gradient G. So they told us we should call it G, right? So Vipex, it depends on what the questioner wants you to call it. In this question, it said calculate the gradient G. So we're calling it G here. right? So again, the gradient is just y2 minus y1 over x2 minus x1. And to find the gradient, you're going to pick 2 points that are on the line. On the line. To figure out the units, you look at what's on the y-axis. So if it's y2 minus y1, then this will be a difference of something on the y-axis because it's y. So what do we measure on the y-axis? On the y-axis, we measure degrees Celsius. And on the x-axis, we measured seconds, which is time. So altogether, it would have been degrees Celsius slash S. Bam. So person on YouTube, I hope you understood that. So anytime you find an ingredient, it's just 2 points on the line. You label one x1, y1, and you label the other one x2, y2. So hope you understand that.
So any 2 points, right? Even if you had choose the ones that you the plot, like the ones that you plot.
No. Here what I'm saying, the points must be on the line. Let me ask that question. This point on the line? So the line I'm talking about is this purple line over here. Is this point on the line? Is this point on the line?
No.
Is this point on the line? See,
No.
you have to read off points that are exactly on the line. So this point over here is on the line, so you read that off. I see that this is another nice point, so I read that off. But the points must be on the line. Understand? It must be on the line.
No, okay.
Otherwise, it wouldn't work. You were from a YouTube live.
Yeah.
Okay, good. You're on the group chat.
Nah, I mean nobody group chat.
What's your name again? I got added to the group chat.
Richard from Guyana.
Okay, big up yourself, Richard. Big up the Guyanese people one time. You guys just send me back a message on WhatsApp and I'll add it to the group chat.
Alright, bless.
No problem. Right? Because the night before the physics exam, I am going to be going for 12 hours for free.
Good.
Yeah. So I look forward to seeing you there. Gonna be going through the whole syllabus if possible. Yeah. Make sure you guys sleep, eh? Because I can't be going. I can't be going. We're gonna be going. It's gonna be very, very intense. So yeah, that's it for today, guys. Take care. Peace and love. If you want to join the Zoom, send me a message on WhatsApp. My WhatsApp number is on my profile, on my TikTok profile. But yeah, guys, take care. Have a good night, guys. I will send this on chat now.
Yes,
Take
sir.
care.
Thanks for your help, sir, and good night as well.
Thanks for
Get some sleep,
your
sir.
Yeah.
thanks for
Thanks,
your
sir.
dedication and your time, so we appreciate it from the bottom of our hearts, sir.
Wait, let me make a little TikTok video. I don't think people realize I started TikTok live. I'm physics live now. I don't think people realize.
Yeah, my camera tweaking, so I don't know what's going on.
Right, check. She went trying to fix it here and thing. Trying to get the huzz.
Nah, sir. Just see, nah, sir. Heck, can I chop right now, nah, sir? Yeah.
Alright, so record all the video. So this was the first physics live. We did all our thermal physics today. Right? All I can tell them anything all I learn.
We learned a whole set of thing on thermal physics. It was nice. It was something good to remember. And open to see more lives coming in and more knowledge being remembered for that physics that coming up.
Yeah, boy. Friday we gotta match them up, right? So I have a question for you. When would I use specific heat capacity formula?
Well, you would use the specific heat capacity formula when you're trying to find the specific heat.
I wasn't, well, you're not wrong, right? But we typically use it when there's a change in.
Well, temperature, correct.
And which other formula would use when there's a change in state?
Just
The
the
latent heat of
latent heat
vaporization and fusion.
Right.
those latent heat formulas.
Yeah.
So I will be seeing you guys tomorrow. And don't forget, day before the exam, we're going to go for 12 hours.
Hey, and
Look forward to seeing you there.
it was nice to learn about the greenhouse effect too.
Yeah, boy. Greenhouse effect. We have a question. What kind of radiation does the sun emit?
Short wavelengths. Short wave radiation.
Short RR wavelengths.
Yes, short wavelength IR waves, which on the EM spectrum, by the way. But yeah, guys, peace and love. Take care. Tell them subscribe. Or they don't know.
Subscribe to Mac Vibes.
I
Stop
always talk.
watching the videos and not subscribing.
Right. Take care, guys. See you in the live tomorrow.